a technical meeting. I will be presenting a little bit about the LASC Cooperation Program and also about the Latin American Space Challenge. It's going to be more or less 5 to 10 minutes. And after that, we will be presenting to you the system design review. And of course, our evaluation committee will be discussing the ideas that the PMOs will be presenting to us tonight. Okay. So before we start, I want to do the launch status checklist with every PMO here in the meeting room. So I will be saying your name and just say go if you are ready to start. Okay? Vinícius.
Go.
Alexandre Goulart. Ixi, esse...
Opa, go.
André Benoit.
Go.
Arthur da Costa.
Go.
Augusto José Silvestre.
Go.
Breno Rosada.
Go.
Bruno Gatti.
Go.
Christopher Deep.
Go.
Eduardo Cavaná.
Go.
Elmo Brandão.
Go.
Felipe Bogaerts.
Go.
Yamato.
Go.
Heloísa.
Go.
Igor Noves.
Go.
Isabela Fontoura.
Go.
João Fleury.
Go.
João Vilas Boas. Larissa Silva.
Go.
Lívia Bartoli.
Go.
Luca de Araújo. Lucas Furlan.
Go.
Lucas Pellegrini.
Go.
Mateuzeira, Mateusão.
Go.
PION. Micaele Oliveira. Moniche Matur. Nice.
Go.
Murilo Faria, Olavo Caetano.
Go. Go.
Pedro Carvalho.
Go.
Rafael Cota.
Go.
Rodrigo Martinelli.
Go.
Sara Roddy.
Go.
Vitor Capácia.
Go.
E Vinícius Fernandes.
A final go.
Okay, guys. I did that because we have in this room 39 people, and here we have just the PMOs and the vice PMOs. There are a lot of people working in this project, so this is huge. It's nice to have each of you here with us tonight. So let's start with our system design review. I will be presenting a little bit about the LASC Cooperation Program. João, can I go? Thank you, João. The Latin American Space Challenge is an event that has been launching rockets since 2019. The first year we had 25 registered teams, 5 countries, 12 rockets being launched, over 350 participants, and more than 500,000 of media impact. So the event was just in its first year, and we had a lot of participants, rockets, and media impact. It was something great, but during the event, we saw things that for the future, it was not so good. For example, we had lots of 1 kilometer apogee rockets. We need something bigger. We need teams working in more complex projects. So this is when we talked with our LASC organization team, and we decided to have a cooperation to have teams from different places, different countries, working together in a new project that they never worked together or worked individually in a project like that. So we have, after that, we had the idea for the 5-kilometer rocket project. So here's just something about how we thought in that. In 2020, before the COVID-19 impact, we had more or less 25 teams registered for Latin American Space Challenge, and you can see in this slide that just 4 teams registered for 3-kilometer apogee rockets. Brazil and Latin America, it's huge. We have a lot of countries, universities, teams, so just 4 working a 3-kilometer rocket was not so good. After that, we start to do some rehearsal. We talked with the people from Iraq and ESRA, the Experimental Sound Rocket Association. In 2020, they accept 150 teams from around the globe. More or less 40% was going to launch a 30,000 feet category rocket. For example, this is more or less 10 kilometers. And in this category, 100% from the US. And it's important to say that only 7% of the accepted teams for 30K was a solid rocket motor developed by students, just 11 teams, even in the US. So it was the time, so now it's the time to challenge ourselves for new projects, like I said before, in a more collaborative way that we can have a cost reduction and time reduction. So why 5 kilometers apogee? It's not competitive, even in Spaceport America Cup or Latin American Space Challenge. It's not a competitive category. The rocket could be launched during 2021 Latin American Space Challenge using the same ground support for a 3-kilometer category. So collaboration plus cost reduction plus challenge, we have motivation and learning. So I want to present the registered teams now from the 2021 Cooperation Program. We have 28 teams from 5 countries, over 300 participants towards a dream, one dream, 5-kilometer apogee. So 22 teams from Brazil, 3 from Peru, 1 from Colombia, 1 from India, and 1 from Paraguay. We have here our HMS Realmaker from Brazil, Minerva, NTA, Grupo de Foguetes de Roraima, Refesto, Dual Rocketeers, Greav, Phoenix Rocket Team, CEPA, Aerospace Peruvian Team, Dark Falcons, Kine Space, Grupo de Foguetes, Gaspar, Tau Rocket Team, Cefab, Isoentropics Engineering, SEB Rocket Design, Antares, Orion Aerospace Design, Bian Rocket Design, Equipe de Propulsão e Tecnologia Aeroespacial, Supernova Rocketry, Luft, Topos, Phoenix, Fibras Técnicas Peru, Clube Aeroespacial F-Puna, Projeto Júpiter. So the mission concept of our challenge, that it's not a challenge, it's a cooperation program. It's very simple. We will have a rocket being lifted off, thrust phase, coast phase, apogee, a drogue, main shoot, and the land of the rocket and the commissioning, recovering the rocket. It's a very simple mission that the PMOs will be talking about in a few minutes. So how the organization structure was formed for the cooperation program. We have a lot of people, many PMOs, many subsystems and systems. How could we organize everything together? So LASC organization is a contracting agency. We deliver the mission requirements, system requirements, and we are the decision makers for the design review. For example, tonight we have evaluation committee here that we will be doing the decision making. We have the isoentropics team represented by Vinicius. He is the project manager and is our contractor. They are the project leader and they are doing the overall project management. And we have the teams, the contractors and, for example, vendors that will make the mission development, system design, production tasks, safety, assembly, and integration. And of course, the Latin American Space Challenge Cooperation Program will be funded by PION and its sponsors. So this is the organization chart. We have the contracting agents, LASC organization. We have the mentors. Tonight we have a mentor here with us, Alexandre Goulart. Good night.
Hello.
Night.
Good night.
We have isoentropics. They are the overall project manager. We have the detailed project manager. It is two systems, the project management and systems engineering and safety assembly and integration operations. And the contractors are divided in 6 subsystems: ground support, propulsion, recovery, avionics, payload, structure, and aerodynamics. So here is our timeline. We start this project in July 2020 with the mission concept. We delivered the system requirements, and now we are in our system design review in the timeline. So we are aiming to launch this 5-kilometer rocket in August 2021. Is our launch window during the 2021 Latin American Space Challenge. From here to there, we have more or less 6 design review. Every single one will be live streamed on YouTube. This is going to be recorded for future projects that every team in the world can be watch and replicate the systems. This is more or less open project. So let me stop talking. Let's start the system design review. Okay. I will be changing presentations. Just give me 1 minute, please. And just a word before, I will presenting the evaluation committee now, before the starting. Tonight we have Gabriel Yamato. Gabriel Yamato is an aerospace engineer. He has working with rockets since 2015, if I'm not wrong. He has launched more than 50 rockets since 2015. He has a lot of experience in this sector, so he's going to he's a part of our evaluation committee. Good night, Yamato.
Good night, Calvin. Good night, everyone.
Okay, we have Alexandre Goulart. He is also a mentor for the cooperation program. He is an aerospace engineering undergraduate. Sorry. He has been working with us at PION labs from 2016. From now, he has launched more than 50 rockets with us. Also, hybrid rocket engines, test and development, a lot of things. He has a knowledge that I think it's, I have no words to say about his knowledge. Good night, Alexandre.
Good night. Hello.
Nice. We have here Victor Capacia. He is a structures engineer. He is working on Embraer. Good night, Victor.
Hey, Calvin. Hey, everyone. It's a pleasure to be here. I'm excited to see a little bit about this system review.
Nice. Thank you, Victor. Also, we have Mateus Cruz and Mateus. Where is Mateus? Mateus Belo and Mateus Cruz. Good night, guys.
Good night. Hello to everyone.
And also we have Isabella Fontoura. She is a aerospace engineer undergraduate from Purdue University. I'm not sure if I said Purdue correctly. So good night, Isabella.
Good night, it's fine.
Thank you. So this is going to be our evaluation committee for the system design review. Now, Vinicius, you have the word. It's your time.
Thank you very much, Calvin.
Oh, sorry,
Thank you very
sorry, Vinicius. I have one more. I forgot. João. Sorry about that. João Pedro Vilas Boas is working with us since 2018. He has a knowledge on information technology systems. I have working with him since then. He is a good and a nice guy that developed our hybrid rocket engine evolved system. So not just it, but a lot of other things. And he is going to be part of the evaluation committee also. Good night, João. Sorry about that.
Good night, everyone.
So now, Vinicius, I think now you can talk.
Are you sure there's no phone, no one left, I guess? Okay. Okay, thank you very much. Thank you very much, Calvin. Thank you very much for all the person and the people that participate in the evaluation committee. Is a great honor to have you here to show the work of the people around. As Calvin said, the Isentropics is the project header of this project, as the subcontractor, and we are powering this cooperation and organizing the teams and organizing the development of this mission, a first here in Brazil, a first 5-kilometer rocket developed and launched in Brazilian territory, and with a plus, because this is an international corporation. So just some curiosities and some numbers about that. We have 8 subsystems that's gonna present tonight. 7 by then. 7 by these subsystems are developed by participants of the cooperation, and these participants, we have a variety of participants. We have undergraduates, we have graduates, we have professionals, we have professors, and we have engineers, and all kinds of walk of life of people. The official start was 25 July as the first gathering of the people of the cooperation, and the 5 August to 2020 was the start of the official channel of the cooperation. And I'm glad to present you the first step in this big process of development called the System Design Review. We have several other steps about the PDR phase, the CDR phase, the project, and so on, so on, so on. But the SDR phase is the first step we must take to define what kind of mission we're gonna persuade, what kind of designs, what kind of concepts we're gonna develop in this mission. And tonight we have 26 participants of the cooperation that are gonna present each one of those concepts about structures, avionics, recovery, payload, aerodynamics, and propulsion. And I wish you all a good presentation and a good night. Please go on. And now I pass the word for Calvin. Calvin, you may run free now.
Okay, thank you, Vinicius. Thank you for your introduction. It's important to say that this is the system design review. It's the first part of a project after the system's requirements are delivered. So let's start with the structures and aerodynamic system design review. I will be asking Augusto Lima to have the word. In this system, we have topos, PTA, Viewmaker, TAU, Clube Aeroespacial F. Puna, and our great friends from Dual Rocketeers from India.
Okay, so good evening, everyone. My name is Augusto Lima, as Calvin said. I'm the PMO of the Structures and Aerodynamics area. If you could please pass the slide, please. Yes. First of all, I'm going to talk about some of the challenges that we had regarding the aerodynamics part. So our major requirement for the aerodynamics is to keep the rocket stability. So the biggest duty of the aerodynamics area is to assure that the rocket will perform a stable flight during its ascent. So of course, in order to do that, according to the general design requirements document that LASC provided us, the static margin of the rocket must assume a value of at least between 1.5 and 2 calibers. Just a quick note here, the static margin is a parameter that depends upon the basically the position of the CP and the position of the CG of the rocket. And it indicates how stable a rocket is. So this array 1.5 to 2 will assure that the rocket will be statically stable from the start. But also, besides that, although a higher static margin indicates a higher condition of stability, if it exceeds by a significant amount the value of 2.0 calibers, the rocket may become overstable. And that is also a problem because the rocket will be considered dynamic unstable. That may be as harmful for the mission as the static instability. And in particular, for this mission, we had some kind of scenarios like the mass of the propellant when compared to the total mass of the rocket is significant. It goes somewhere around 27% of the total mass. So as the rocket consumes the propellant, the CG will change a lot its position. And also we have to consider that the center of pressure will change also a lot its location because of the effects of transonic and supersonic flows acting upon the rocket's aerodynamic shape. Another information here. We are expecting the rocket to achieve a maximum speed of over Mach 1.2. Besides that, we are also aiming to reduce the total drag of the rocket, although it's not a top priority because, of course, first we want to make a stable rocket because of safety. And then we want to make an optimized and efficient in aerodynamic terms rocket. Because of course, aerodynamically efficiency will increase the effectiveness of the thrust produced by the motor, and that is something totally desired. Okay, so now we'll go through the components of the aerodynamics area, okay? So I guess Bruno, if you could, yes, I guess Pedro now will talk a little bit about the fins.
Yeah, can you turn back the slide? Yeah, thank you. Now talking about the fins diameter. The fins are responsible for the rocket stability. So we consider the two most critical flight moments to the stability to take the design decisions. The first one is the launch rail departure, when the rocket has a speed much greater than the wind's velocity, causing the formation of an angle of attack. And the second one is the transonic flight, when the formation of shock waves will decrease the fin's lift coefficient, causing stability loss. Having in mind these two flight moments, it is possible to choose some fin geometries that will allow us to assure stability and optimize the rocket's aerodynamics. First, the overall geometry was set as trapezoidal due to the manufacturer viability and the existence of simple models like the Berman equations that will allow us to optimize the fin's dimensions with low computational cost. The trapezoidal geometry can also delay the shock waves due to its sweeping angle, decreasing the wave drag coefficient. The second design decision is the fin section geometry, set as hexagonal or biconvex. This choice was also made considering the transonic regime, when the shock waves formation will decrease the fin's lift coefficient. As these geometries have a sharp leading edge, it is highly efficient on transonic and supersonic speeds, which will prevent stability loss and reduce the wave drag coefficient. The number of fins were set as 3 or 4, as 3 is the minimum number required to ensure stability, and in case of a scenario in optimization phase, where the 3 fins are too big, present a high drag coefficient and low flutter speed, 4 fins will be used instead of 3.
Good night, guys. I will present the. You can go on, man. Okay, thanks. Well, I will present the manufacturing of the fin. Okay, we chose the sandwich manufacturing process because it's a possible way to build it, and we can optimize the fins following the theory presented before by Pedro. The process consists in using balsa wood interlayered with fibers, like you can see on the picture on the right. Okay, you see the balsa. Above of balsa will be a layer of fiber. Then we use balsa. Then we use fiber, and go on. Okay, let's go. We choose the two kinds of fibers to decide it: carbon fiber and fiberglass, because of the mechanical analysis provide this. And one consideration we had is carbon fiber is a good option because it needs less layers to be stronger than fiberglass. After an analysis shown by our friends from Tau, Topos selected these two materials to be the manufacturing materials. Okay, the principal fiberglass we are working on is the fiberglass type E, and because it's easy to find here in Brazil, and it's cheap. Okay, not expensive, and has some good properties. We can see it like high strength. Okay. And the carbon fiber we are working on is the RC200P, because it's also available here in Brazil, and it's have a very good mechanical properties. Okay, thanks.
Now I guess Murilo will talk a little bit about the boat tail. If you could pass the slide, please.
Hello, guys. So we will continue with the boat tail design. And I will talk about the geometry and thermal considerations, and Galete will talk about the materials and the trade-off analysis. So we choose the trunk cone geometry, and that should reduce the profile drag, and furthermore, it makes the calculation and the manufacturing process much easier. So the thermal considerations, we can say that during the burn time, the temperature around the nozzle should reach high levels, which could harm the boat tail material. And therefore, the thermal outputs about the nozzle are critical for the boat tail subsystems.
In relation to the materials, we can say that because of the high temperature around the nozzle, it was necessary to choose a material that could resist the maximum temperature reached on its surroundings. Moreover, this material needs to have a good mechanical resistance and low density, so it can resist the imposed stresses to the boat tail and at the same time doesn't add too much weight. So based on that, we have chosen two preliminary materials, which are aluminum and stainless steel. And about the trade-off analysis, we have to analyze that at the same time that the boat tail reduces the profile drag, it also increases the overall weight of the rocket. So because of that, the CFD analysis will be needed to see if the drag reduction is worth in comparison to the weight added to the rocket, and then conclude if we should or not build the boat tail.
So we can proceed with the presentation. That's all.
Okay, I guess I'm not sure, but we had a okay. So I'm gonna talk about a little bit about the structures part, the requirements and the challenges. So our major goal here is to produce both external and internal structures that are safe, easy to integrate, and that will allow the other subsystems to perform their own functions in, of course, the best way possible. So the first major requirement of this section is to assure that the rocket will not perish when subjected to the internal and external loads during the whole flight. As you can see, our main concerns are related to the expected weight and maximum acceleration. The dry mass will go around 27 kilograms, and the maximum acceleration I didn't put on the slide, but it will be something around 16 Gs. I think the propulsion subsystem will talk a little bit more about it. Also, we're aiming to create a design that is easy to integrate, that will meet the other subsystems needs, which is honestly always a challenge because we have to conciliate many demands. Can you pass the slide, please? Okay, so now I'm gonna call Lucas. He's gonna talk a little bit about the motor models.
Okay, so the first thing that we thought on the structures part was how to pass the thrust from the motor to the rest of the rocket body. And to do so, we thought in a bulkhead, in just one bulkhead over the motor. We thought in two different designs, actually. The first one is an open top bulkhead. This design actually have the advantage of less mass than the other, but we need more screws outside and have less screws outside the fuselage. But some problem with that design is that it's harder to assemble because there are some screws going inside to outside the fuselage, so it'll be a little harder to assemble, and have less thermal isolation because the motor don't have any protection and the payload bay will be over the motor. Can you pass, please? the slide. Okay, thanks. The second idea of the bulkhead is a closer-top bulkhead. This bulkhead is actually simpler than the other, but doesn't have any screws attaching the motor to this bulkhead. So we have to do something to attach this motor and lock them to slide down the z-axis. So the most issue with this design is that have more screws outside the fuselage, but have some advantage compared to the other. It's easier to assemble and it's easier to use a thermal protection because the toppest part of this bulkhead actually is a plane. So could you please pass again? Okay. The second thing that we thought is about the main coupling. So the rocket will have a main coupling over the payload bay, and we thought in the simplest and easiest design as possible. We thought in two metal rings, probably made of steel, because we have this is a critical point of the rocket, and the steel will enable us to build a really thin ring, and that will enable us to attach permanently these rings on the fuselage, so it will reduce the damage made by the rolls on the fuselage. Could you please again pass? Okay. About the fuselage and the external fuselage, under the main coupling, the fuselage will be entirely made of some fiber without division. We consider glass, carbon, aramid, and a hybrid fiber of those ones. The choice will depend actually on the resource that we have to manufacture the rocket and the mass of this structure. An evaluation will be necessary to define the fuselage thickness over the structural bulkhead to support all the loads, because all the loads will pass to the fuselage over the main bulkhead. If it gets too massive, an internal structure will be necessary on the payload bay to support that loads. Actually, all the designs of payload that will be presented after some time can be integrated with that design that I'm showing for you guys. The materials that we are considering are actually basically fibers, or like I said, and the production of the fuselage production will be made around a mold with fiber and epoxy in such a way that we can remove the fuselage entirely. And the fins will be attached to the fuselage with epoxy with help of some mold to align them correctly. We choose that because both materials of the fuselage and the fins will be fiber and epoxy and can attach the fiber really well. So I think now is Livia.
Okay, so good night, everyone. Talking now about the main avionics bay, it would be placed at the middle of the body between the payload and the recovery sections. The current idea is to place all components inside a 3D printed bay, where the bay sides would have linear rail guide carriages that shall slide along 3 linear rails that would be fixed on the internal side of the fuselage tube by the internal bulkheads. The rail guides will provide a locking system which can lock the avionics bay at a certain height as well as prevent rotation. It has also been considered making a sideway hatch window to access the avionics from the outside. With this, it won't be necessary to disintegrate the bay for pre-flight checks, and therefore the system will allow an easy and effortless integration of the bay to the rest of the rocket, and it is a more practical design. The problem with this concept is the camera mounting, as it would have to be near the payload and coupler or near the recovery section, which are very unsafe locations, or try to put it through the payload section. But this concept should allow a window or a transparent tube, for example. So to solve this issue, we have made a concept where the avionics is split and the camera goes under the nose cone. And I'll get in details soon, but if you could go forward, please. Talking a little about recovery. On top of the avionics bay comes the recovery section. The structure's point of view of the recovery system is very straightforward, as the whole system will be still presented. The first coupler of the rocket is going to be between the nose cone and the recovery system, and that's where the separation is going to be made. So due to this design, it is necessary to have a closed upper bulkhead to protect the upper avionics when present, and open coupler to fix on the recovery fuselage that allows the ejection of the parachutes. Another open bulkhead with a U-boat in the middle of the section might be needed for the main parachute deployment system, and the fuselage of the section has to be resistant enough to withstand the axial stresses and the pressure that causes the separation, and possibly the heating depending on the actuator used in the recovery. Can you go forward, please? Okay, so going back to the avionics modules of the rocket, we have also considered a design that splits into parts. The proposal of this complementary design is to place a printed circuit board and a battery inside the nose cone, giving the space available. The pre-selection of material for the current proposal of the cone using fiberglass and the foam core is perfect to ensure protection of the components. The camera for this design shall be placed on top of the nose cone shoulder, where it is believed to be a great field of vision during the whole flight. So there, the external fuselage, as of now, would be a transparent tube, giving a transparent view from the camera. But as all transparent materials that we have researched are not very strong, we would need to reinforce the area with 2 rods, like as a structure, on the sides of the camera, hopefully on the blind spots, so we don't get in the way of the video. And this concept also presents a proposal for the primary recovery system, in which the first trigger mechanism would be placed at the base of the nose cone shoulder, which will be mounted on the closed upper bulkhead of the nose cone, as mentioned before. Thank you all.
So now, before we go into the whole conceptual designs, I'll call Arthur and Elmo to explain a little bit about the nose cone. We've actually made a slide about the nose cone. I think there was a problem because the slide's not there. So please, Arthur, if you could tell us a little bit about the nose cone.
Yes, of course. Well, first of all, the nose cone is the component responsible for the first contact of the rocket with the airflow. For that reason, the cone's geometry must grant the minimum drag possible, but don't disturb the rocket's stability. The geometry chosen for this project was the tangent ogive because of its wide use in research and sounding rockets, leading to a very complete and complex database. Furthermore, it features a good efficiency in both subsonic, transonic, and supersonic regimes, all of which the rocket will experiment. Other geometries could provide better performance, however, may not be feasible due to the lack of experience and manufacturing capabilities. For the aspect ratio of the cone, it was defined as a value between 1.5 and 4.0. Even though it sounds like a small value, impacted with a larger drag, it lowers the static margin of the rockets, allowing for the use of smaller fins, reducing the drag in that way. Both effects will be considered during the optimization of drag in later phases of the project. The minimum value of 1.5 was defined by the limitations of the database, while the maximum value of 4 was defined by the manufacturing limitations. And now Elmo will talk about the manufacturing of this cone.
Well, Elmo here. Once we get a preliminary design, the following question naturally is, how do we make it? Because that implies several other questions about fabrication, such as access to materials, its costs, can we assure if it will be easily alignable to the rest of the fuselage axis, and how much time does it get to be done? Can we make a prototype, or can we make it? Does the prototype can be easily scaled up? So trying to answer those questions, we immediately realized that turning the nose cone out on a solid block on a lake would not be viable because that's really very time consuming. It's really hard to get lathes large enough for machining such a big piece, because if you get the ratio of 4, that means that the piece will be almost 3/4 of a meter long. So that we really we immediately had to figure out another way to do that. So we went along with the composite fabrication. But once we were really intended to get quick results, we had to skip the conventional conventional type of working with composites, that the mold type, the molding type, that you make a master mold that goes outside, and have to make several jig pieces to make it in place, to make the resin waiting for the resin to be cured. So taking the example from scaled composites, which make the spaceship one back in 2004. We are studying using the modulus process that we make a foam, a polyethylene or polyurethane core embed with coated with a composite layer that you lay up on it, so you don't have to remove the mold. You don't have to mind with demoldants and other kind of demolding issues. Just like you only have we were able to check the result 4 hours later after the resin cures. So I came up a way to fabricate the nose cone using a lathe, using a threaded bar as a backbone, to assure it will be aligned to the rest of the base, and we really get really good results, and that really goes steady with the secondary design for avionics, with the nose cone housed avionics, because that burrow, that cavities really looks like viable, making that way.
Okay.
Thank you.
Please go forward. Now we're going to present you guys the complete conceptual designs. You notice that we decided to make an approach based on major changes regarding the whole configuration of the rocket. But please feel free to comment on any other minor aspect that we just showed you. So for the first design, I don't know who's in charge of the slides, but I'm going to make you work a little bit right now. Please go forward. So for the fins, we have basically the same informations that we already gave you. 3 or 4, trapezoidal geometry, hexagonal or biconvex cross-section, material, also core probably. Please go forward. once more. Yes, now we have the nose cone, so ogive tangent, body made of composite material with metallic tip, and an aspect ratio between these values there. Also, the materials, as Elmo just said, will be composite with metallic tip. Please go forward. About the boat tail, same here, trunk cone geometry, materials, aluminum or stainless steel. Please go forward. Now, there are the major parts of the design. Here we have a design with the avionics divided. So we have the first section there just beneath the nose cone and the other just beneath the recovery. Please go on. Okay, so the recovery section, as Livia just mentioned. Oh, and just one quick note here. The recovery section and the payload section will be better explained on the respective subsystems presentation. Okay, please go forward. Here we have another unique aspect of this design. For the propulsion section, this design has a bulkhead with an open top. Please go forward. And we have the payload section that I said that is going to be better explained during the respective subsystem presentation. Please go forward. So this is the first design. Here we have basically avionics divided and bulkhead with, propulsion section with bulkhead with an open top. Please go forward and I'll show you guys the pros and cons. Oh, of course, and we have the coupling systems that contains 2 couplers. So in the next slide, I'll show you guys the pros and cons of this conceptual design. Okay, so the pros, they were already mentioned. Due to divided avionics design, we will have a better position for the camera and a better use of internal space. And due to the open bulkhead design, we'll have higher structural efficiency, reduced mass, less screws placed on the outside of the fuselage as well. For the cons, due to the divided avionics design, we have some sort we'll have to add some sort of shield to protect the avionics from the ejection system, depending on which ejection system the recovery will use. And the nose cone must be made of fiberglass in order because the camera there will have an antenna, and other materials like carbon fiber and aluminum are terrible to put things with antennas because it affects the communication. And the cones, due to open bulkhead design, will probably need a thermal protection, and it's also a little harder to assemble. So let's go to the second conceptual design. You can go through this part. So the fin is the same thing. The nose cone is the same thing. The boat tail as well. Here we have a design in which the avionics is located only at the middle of the fuselage. So we only have the main bay. Please go on. The recovery section is the same. And here at the propulsion section, we also have an open a bulkhead with an open top. We'll see that in future designs, this will change. The payload section is the same. And the couplers is the same. So I'm going to give you guys the pros and cons of this design as well in the next slide. Okay. So basically, the only thing that changes are the pros and cons due to United Avionics design. So this design allows us to access more directly the whole avionics components. So we only have to make like one move to like have access to the whole avionics. But about the cons, the camera has a worse position, and as Livia said, it's not a good place for the camera. Regarding the pros and cons to the due to the open bulkhead design, I just mentioned them on the previous design. So let's go on to the third conceptual design. This is not the last one. So the fins are the same. The nose cone is the same. The boat tail same. Just saying again, you can comment on every single detail that we just talked about. Oh, just please go back to the avionics. The avionics in this case is divided. So we have the second here designed with a divided avionics. Please go on. The recovery system is the same, and you see that now with the propulsion, please go on just a little further. Yes. So about the propulsion system, now we have a bulkhead with a closed top. Please go on. I'll tell you guys all about the pros and cons in the next slide. The payload is the same, and you see the couplers is the same. Yes. So let's go to the pros and cons. So you guys already know the pros and cons due to the divided avionics design. And about the pros regarding the closed bulkhead designs, we have that this design is easy to hold as a thermal protection, and it's easier to assembly and to solve issues. We have more direct access to it. And the cons are that this design is considerable, demands a considerable numbers of screws outside that may affect aerodynamics and also structural properties of the fiber. So let's go to the LASC conceptual design. Okay, you see that this design is a combination of the others. Please go on. So the aerodynamic section is the same. Here at Avionics, we have just like the second, I guess, the second conceptual design, we have the avionics only at the main bay, at the middle of the body. Please go on. The recovery section, the same. And now at the propulsion section, we have a closed top bulkhead. So this time we have United Avionics and a closed top bulkhead at the propulsion section. You can go on, please. And I'll tell you the pros and cons of this design. Okay, so payload, and now the couplers. Please go on. You can change the slides, please. So just again, the pros and the cons. It's the same pros and cons due to the United Avionics and due to the closed bulkhead design. So just saying it again, so due to the United Avionics, its practicality to access all components of the avionics. It's also a simpler design, and but in the other way, it's a worse position for the camera. Due to the closed bulkhead design, it's easy to hold the thermal protection, and it's easier to assemble and solve issues. In the other hand, this design demands a considerable number of screws outside that, as I said before, may affect the aerodynamics of the rocket. So this is it. These are the 4 designs that we've made. again, you guys can comment on any minor detail of the designs. We just didn't count the multiple combinations of them, because we would give you a lot of designs, and I think we wouldn't have time to evaluate all of them. So that's it. Thank you very much.
Thank you. Nice presentation, nice work. It's a pleasure to watch. It was a pleasure to watch your presentation, your team presentation. It's a nice project. It's a nice group of designs. Now our evaluation committee will talk about your designs and ask some questions, okay?
Sure.
Okay, let's start. I did some notes here. Let me ask if Gabriel, do you want to start talk?
Yes, sure, Calvin. Thank you. First of all, thanks for the presentation and the initial designs. It was really good and amazing work that you guys did. And just a quick comment for starting with the static and dynamic analysis of the aerodynamic stability. I just would like to check with you guys that try not to be limited to of the static margin to be only between 1 and 2. Try to set a minimum like 1.5, and the maximum try not to be limited on 2, and do some other analysis, especially using wind speed data from Cape Canaveral, where it will be launched. We have some data there, and Calvin can also provide more data about it, and try to analyze better the angle of attack, and also the dumping ratio. Sometimes we saw the rockets that goes up, lift offs, and the trajectory is kind of a snake, you know, it's going right and left, right, left, usually after the burnout of the engine on their motor. So ideally try to analyze the natural frequency, the dumping ratio, and then you can set up better also the CP position and the static and dynamic margin. So that's my comment, Calvin. I think we can move to the next comments.
Okay, nice. I just want to say something for your team, the structural and aerodynamics team. Next time, it's going to be good if you have at the end a table with the difference of each design. It's going to be easier for us to talk on the concept designs, not like moving from each slide to other slide. So it's a recommendation for the next design review, okay? Gabriel Yamato just talked, so Alexandre Goulart, do you want to talk?
Yeah, sure. So first, thank you also about our presentation. Pretty good presentation, pretty good work. Of course, it would be a good thing to get a comparison table at the end, but that's fine. I think we can tackle each difference alone, so we can reach the preferred configuration. So I will start commenting on the boat tail. So most of the configuration, no, not most, I think all of the configurations have a boat tail, and specifically made out of aluminum or stainless steel. Well, the thing is, both of these materials would make a part a pretty heavy part, and as far as I know, usually it doesn't give a justifiable amount of drag reduction to justify this this weight increase. So I would suggest two things, or think about maybe
a 3D printed, not suggesting, but also asking what if you have discussed, or if it's if you talked if it's viable or not, a 3D printed, even with the heat load and the possibly the impact with the ground, with the recovery, or simply doesn't have a boat tail. Or what are your thoughts about it? And like, have you, first, to be clear, but have you talked about the possibility of a 3D printed one? Maybe.
Yes, in fact, we did. In fact, at Topos and at basically all the other teams that are part of the aerodynamics area, they've done previous rockets with boat tails made of 3D printed material. And we actually we didn't consider 3D printed material exactly because of the thermal issues that may because the 3D printed material isn't really doesn't have much thermal capabilities, let's say like that, and the informations, the preliminary informations that we got from the propulsion team is that it's going to be quite hot at the nozzle, and we probably think that a 3D printed boat tail wouldn't be able to sustain the temperature there. But yes, we are going to make this analysis, and it's and thank you very much for your advice, and Gabriel as well. We're going to keep that in mind. Of course, if the boat tail is absolutely useless, at first sight we'll discard it.
Okay, so everything depends on the aerodynamic simulations then.
Yeah, exactly.
Okay, that's fine. So the other point is about the also another thing related to thermal problems. It's about the fixation ring of the motor, and you have two designs, right? The one that's open and the other that's closed, and therefore much heavier. Well, I know that's a concern, but I believe there may be simpler solutions. I'm going to give an example, but well, I just thought about it now, so it's just an example. So maybe less like lighter possibilities for this problem. For example, if you have a balsa circle fixed with screws over the open aluminum part, maybe it would be enough for the heat load, and also it would be screwed to the part, so there will be no problem fixating it. So just I think there may be simpler solutions with the same or even best outcome. And also, if you have you tackled some other solutions, are you thinking, what are you thinking about that? So maybe I should, well, that's more of a suggestion. Maybe I should tackle already my last question, my last comment. That's about the linear rails. The thing is, I don't know if it's just this name is just being used as a reference, but linear rails are very specific mechanic components and also very expensive. So they wouldn't, I believe they wouldn't be quite as adequate for this use. Maybe it would be possible to use a simple aluminum T-track that you could fixate to your fuselage and to make an easier fit of avionics or anything else, or maybe 3D printed rails. I don't know. I believe linear rails are way too expensive and not exactly adequate for this use.
Thank you, Alexandre. Let's go on. Victor Capacia, do you have any comment?
Hey, Calvin, yes. First of all, I wanted to congratulate everyone for this presentation. I think it was super rich and so nice to see different nations working on a big project like this. And I think since I'm the structure guy, I think Augusto José presented about the structure dimensioning about the rocket. And you talk about your dry weight prediction and max acceleration. And I would like to ask you if you guys are planning to making some hand calculation for dimensioning the rocket, or maybe developing a detailed model, maybe finite element, I don't know. How you guys are planning to attack this structure dimensioning problem, Augusto?
Well, at this point of the design, we only have like preliminary information from the other subsystems and from our own as well. So we weren't really able to do much detailed analysis regarding the mass. Of course, we've got the prediction from the subsystems. We added with our own predictions, and then we got the expected dry mass. We got it basically doing hand calculations and using open rockets and CAD models. That's what we've done until now.
Nice.
About the maximum acceleration, this was given to us by the propulsion subsystem and initial estimations that they've done.
Nice, Augusto. Thank you for your answer. And I think just a tip for you guys, since this is a rocket that probably will be launched, of course, compression loads are the main dimensioning loads for your rocket. But I would say for you guys to try and develop different load cases for you to hand calc or maybe use on your detail model, because since it is mainly compressive loads, but actually when you have parachute separation, you also have big tension loading. When your parts are coming down, maybe a little bit of shear. So since weighting is it's a really important subject in this kind of project, when you consider many load cases, you can, if you have accurate load cases, you can really reduce weight or control your weight in CG. And congratulate everyone. I would like to congratulate everyone for this project. It's really good. Thank you, Calvin.
Thank you, Victor. Let's go. Isabella, Mateus, and Mateus Belo, do you have any comments? Please go on.
No comments.
Thank you, Isabella. Mateus?
No comments.
Mateus Cruz?
No comments on this section.
Okay, thank you so much, guys. I have some comments. Like Alexandre said, I'm not comfortable with the linear rails. I suggest a redesign of the concept. I think the rails will increase the mass of the component system, and the trade-off is not so good. You can use 3D printed interfaces or components that will be lighter and easier to integrate the rocket. I'm saying about the integration, assembly and integration right now, because the linear rails and things like that are very complex and difficult to integrate on the fuselage. And this may be some a decision that we need to take right now before we go to the next step. So I really recommend to redesign and not to use the linear rails, okay? The second comment that I have is about the boat tail. I think that the trade-off between aluminum or steel part to the 3D printed component, it's something that you should rehearsal, because we know that the nozzle will be very hot, of course, with the exhaust gases. But if you use some thermal protection or thermal layer between the 3D printed component and the nozzle, it could be something good instead of using aluminum or steel parts. The rocket is going to be launching to a 5-kilometer apogee. So if you have every part lighter as possible, it's going to help a lot the propulsion guys. So I recommend to think in the 3D print boat tail for this case, or in some thinking about not using a boat tail. João, do you have any commentaries?
Some people in the comments from the YouTube live stream are asking about mass concerns. So each subsystem has a mass budget to work with. And does the rocket itself has a min or maximum weight? These are questions from the audience.
Okay, I think both questions are from Tan Dameno. Thank you, Tan, for watching our system design review. I will ask Vinicius Fernandes from Isoentropics and Augusto Lima, the PMO, if they have any a mass budget for the structure team. I'm going to say from the Latin American Space Challenge part, we do not have any requirement for mass in each system. So I want to listen Vinicius and Augusto.
Augusto, could you start?
Yes, sure. In fact, we don't, for some reasons. First of all, this is a unique project. I guess it will be the first 5-kilometer Brazilian rocket. So we're not quite sure how the mass will go, but it is a concern indeed to make this rocket as light as possible. So I'll by the way, I like to thank Calvin and Alexandre for the advice on the boat tail, because surely we will like to save as much mass as possible. But no, we in fact don't have a limit, basically because the other subsystems are as well making new studies and studying of what they'll need, what mass, for example, regarding the propulsion, they're still studying of how much mass they'll need of propellant and stuff like that. That will surely impact the rocket's mass. So by our part, no, there isn't. But yes, mass, it is in fact a concern of ours.
Also, if well, I'm sorry, I'll talk after you. Sorry, Vinicius.
Oh, thank you very much. Just complimenting, sorry, it's not the word, but just adding what the Augusto just said. The system engineering team have been working in the adjustments and tinkering between the designs, and we are working with estimation of 25 to 30 kilograms of a dry rocket. And when we say dry rocket, is a rocket without the fuel. So 25 to 30 kilograms we are using to estimate the payload, the recovery system, and even the allocations. Thank you.
Also, I would like to comment, answering in a system engineering requirements perspective, we don't have a specific number set for a maximum or minimum weight, but as the requirement as are written in the adequate document, we have to integrate this rocket with the defined launch rails. So we have limitations. They're not explicit number, but if the concern arise with integration to any kind of operation, I believe there is a specific requirement concerning transport of the vehicle itself. So there's not an exact number, but it is inside the requirements. Thank you.
Thank you, guys. Let's going to finish this part. I just have two more comments. The first one is audience comment from Lex Machado. He asked us about the attachment of fins and bow tail attachment. Augusto, I think the attachment was not rehearsed in this part of the preliminary design, in this conceptual design, sorry, correctly?
Yeah, actually, we in fact addressed it. Like we didn't dive into it, but we addressed it. We have some designs regarding that. If Lucas, I think he's more into that. He likes to comment on something, but regarding the things, Lucas, I don't know if he tries to say something, but regarding the things, we'll probably just place it using epoxy and also using fiberglass to attach them to the fuselage. This is one of the ideas. We're still studying them, and I'm not sure if I'll be able to explain the attachment of the bow tail without an image, because it will be fixed, because it's a really particular way to fix it. It's a really clever, if you allow me to make this compliment, but I don't think I can explain it quite, because it's anyways, we're still studying the ways to do it.
Okay, thank you, Augusto. I think you answered the question. So let's finish this part. I think we talked a lot about the conceptual design of the structures and aerodynamics for a conceptual part in the system design review. I think all the evaluation committee has said a lot of recommendations and suggestions. Based on that, I would like to say that you have a lot of work to do after this meeting. Also, I feel more comfortable with a open bulkhead. So I don't remember all the conceptual designs, each one, but I think if you go with a open bulkhead using a thermal protection with the I think it's going to be good for our project. Okay, and finally, I think we passed over all the structure and aerodynamics presentation. So any other comment, guys?
No, I think we can move.
Okay, so homework for the structures and aerodynamic team is to rehearsal the things that we said. Vinicius will be addressing you guys with all the comments that we did, and you will go to study our comments, and you can go focusing to one of the concepts that is aligned with everything that we said, okay?
Okay, I just like to thank all of you guys. I just took note of every single word you just said. Really valuable advices. Thank you very much.
Thank you, thank you. It is just a final suggestion is for couplers, use aluminum, okay? Not steel, aluminum. So let's go to the next part. We finished the aerodynamic and structures part. So we passed all the pros and cons of the conceptual designs. They talked and present to us 4 concepts, and we did our comments. Now I will pass the word to Vinicius and about the propulsion system design review from now.
Thank you very much, Calvin. Now we are going to present the propulsion system design review. Felipe Bogaerts and Igor Noves will bring us the designs, the conceptual designs to power our rocket until the 5 kilometers apogee. Felipe and Igor is with you now.
Okay. Good evening, everyone. Good evening, everyone. My name is Felipe. I am the Vice PMO of Propulsion Subsystem, and I am from Supernova Rocketry, and I study electrical engineering.
And I'm Igor. I'm the PMO of Propulsion Subsystem, and I'm from Minerva Rockets, UFRJ, where I do mechanical engineering undergraduate. So I think we can go to the next slide. So for this presentation, we're gonna me, Felipe, we're gonna show me, Felipe, Andres, and Christopher are gonna show the propulsion, how the propulsion team is working, and our 2 conceptual designs for this project. Andres and Christopher, do you wanna introduce yourselves?
Good evening, everyone. I'm Andres, and I'm team leader of Tau Rocket Team.
Good night. Good evening, everyone. I am Christopher. I am from Orion Aerospace Design.
We can go to the next slide. So, in this presentation, I thought it would be really important to show how the propulsion subsystem is organized and what we've been doing to make this project flow as smoothly as possible. So the first part is going to focus on how we divide our tasks, what are our main objectives, and what tools we use to plot and to structure those objectives. And of course, the second part will be focusing more on the technical part of the project, where we're going to propose the design, show the trade-offs, and hopefully we could use that to make a more informed and optimized decision for this specific task. You can go to the next one. So the first thing me, Felipe, did when we got the PMO position was to think how we could make such a big project work with so many people from so many different places and backgrounds. And for that, we took the propulsion subsystem and divided that into sub-assemblies or departments, 11 of those to be more precise. 7 of those are critical to the project, and 4 other ones are kind of extras, that we thought would be a really good opportunity to establish a methodology so that later teams could use the work we've done on their projects. As Vinicius or Calvin said before, this cooperation is a really great opportunity for other teams to be inspired and to get access to resources that some teams take years and years to develop. So we thought that including those things would be a great opportunity. The departments are internal ballistics that take care of the propellant geometry, nozzle design optimization, and how the thrust and pressure curves will develop over time. The structural projects will be responsible for doing the CADs, the computational integration of the projects, do the hands calculations for the structural project as a whole. The structural analysis will serve to validate the results of the structural projects by means of computational simulation, and be a separate team from the structural projects so that we don't have any kinds of bias. The propellant manufacturing team that will be responsible for developing the techniques to manufacture the propellant and be responsible for doing that. The igniter and kinetics will be responsible for developing igniter grain and analyzing the chemical kinetics of the propellant. The thermal analysis team will be responsible for doing the correct dimensioning of our thermal protection and making sure that we won't have any kind of failure due to thermal loads. And of course, part machining will be responsible for getting the structural project and making it a reality. And in the extra departments, we like to do a burn rate analysis. Our first thought was to do that with a team that could have access to a crowd-for burner, so it could get the ballistics constants of the propellant, but that was not possible. And we still have this department who's going to develop a series of 1 ATM burn rate tests. The fluid flow would be responsible for doing a CFD of the motor. That's a really complex job, and have a team dedicated to that. Pressure relief system, in case that we have overpressurization of the casing, we have a fail-safe mode. And explosion and shrapnel, in case we have a total failure, we could estimate the debris dispersion and establish a safe radius. So the factors that we took into account when doing the subsystem allocation was previous team experience, interest of each member participating in the project, the proximity for tasks that includes tests, manufacturing, and communication.
Igor, are you there?
We lost Igor for a second or more.
Felipe, please go ahead.
Yes, I think Igor is down. I will cover his part of the presentation. So I think he was talking about the geographical proximity, and we chose this as a criteria because it is very important for the tests and all those tasks that involve mechanical parts. This is the final subsystem task allocation matrix. So you can see we got 3 teams on the major positions of each department. We call those subdivisions departments. And we have a main developer, a co-developer, and a second co-developer. So the main developer role is to kind of lead the department, and the main developer will kind of also manage the department. The co-developers will play also a huge role as technical members and other management categories. I think Igor is back, so I think you can pass the slides and he can talk more about.
Yeah, I'm so sorry, guys. That won't happen again. So yeah, after establishing those, which team would do what, we decided to do a series of roadmaps that could explain the project better and help everyone visualize what are our goals and objectives at each step. And again, I think it would be a really cool resource for teams that are starting out that don't have a lot of experience with propulsion, that they can see really fast and easy what are the steps to do a solid rocket motor. We did 4 of those roadmaps. The documentation roadmap, which establishes which are the deliverables for each design phase. Something that I encountered inside my own team in Naval Rockets when I was starting was a series of difficulties to understand what are the design reviews and what is expected from each design review. So doing that specific for the propulsion, I thought would be a good way to communicate that with our collaborators. The motor structure design roadmap that establishes which are the steps necessary to design the structural components of a rocket motor, and the motor propellant design roadmap, which establishes the steps for correct propellant design. Also, we have an ongoing roadmap that we are doing as we go along the way of the propulsion project management. Me and Felipe are seeing what's the things that we are doing, and the things that we are increasing the number of items in this roadmap as we go along the way, and we think, oh, that's the right decision, let's put in the roadmap. Oh, that wasn't so efficient, we're gonna not put in the roadmap. So we can go on to the next slide. So this is the documentation roadmap with the primary deliverables of each design phase. And I'm not going over all of those, just on the SDR. We have to deliver a propellant composition, a diameter definition, total impulse estimation, mass estimation, length estimation, and structure architecture. So yeah, that's a spoiler of the things that are going to propose to you today and evaluate as we go. Can go to the next slide.
So let's talk more about those roadmaps. In order to organize the activities inside our own subsystem, we made some roadmaps that will register and guide our steps during this task. Here in this slide, we have a roadmap of the structural design of a high-power solid rocket motor, and it shows each step taken since the beginning of the project until the manufacture and assembly stages. It also shows interactions with other subsystems and with other departments of the propulsion subsystem. You can see the dashed blocks in green and in red in this case. By looking at the roadmap, it is possible to see that the structural design was divided into 2 general subtopics: the nozzle design and the combustion chamber design. These were further divided into several other more specific activities and topics in chronological order, and until they eventually coincide into one objective. You can see the last objective is the manufacturing and design and assembly of this roadmap. Also, interfaces such as rocket internal diameter, propellant core area, heat generation, and chamber pressure all must be considered when designing this part of the project. So these considerations, these factors must be considered when designing the structural part of a solid rocket motor. You can go to the next one. So here we have a propellant design roadmap, and this follows a similar trajectory from the last roadmap, being divided into propellant composition and internal ballistics. Since these subtopics, inside these subtopics, the propellant geometry, kinetics, chemical characteristics, thermodynamics are considered. As an interface with other parts of the rocket project, heat transfer and maximum allowable acceleration are both very important aspects that shall be accounted here. Can go to the next one. So here we have a propulsion project management roadmap up to the SDR. And this roadmap shows the steps that the propulsion subsystem leaders are taking in order to register from a chronological order all of the important tasks and system engineering files, important meetings, important management strategies, and important gatherings. So in this roadmap, we can see the resource mapping that we talked about previously, the department division, the task allocation, some management files, such as the decision matrices that we will talk about further down the presentation. And it is important to note that this roadmap will be in progress until the end of the project. So as me and Igor take steps forward in the project, this roadmap will constantly grow. So these blocks, they do not represent a desired activity. They represent what was actually made inside the subsystem. And of course, this can be used by less experienced teams and as a sort of a general guide for this subsystem project management. You can pass. So some design constraints were considered in order to fully integrate our motor into the whole project. We divided them into our own constraints inside the propulsion subsystem and the constraints regarding the interface between the motor and the general vehicle. This slide shows the subsystem interface design constraints with other subsystems. And the data here was gathered from the structural, recovery, and avionics subsystems. So we designed our subsystem to achieve a maximum acceleration of 16 G, a maximum velocity of Mach 1.4 as a local value, as the Mach changes with altitude, and the maximum motor diameter of 150 millimeters, including screws or flanges, because the current design of the structural part has a 160 millimeter external diameter. So another part that is very important to consider, the design constraints of the erosive burning. Erosive burning is a pretty negative phenomenon, and if it escapes the maximum values, and it makes the burn rate unpredictable, and it's very undesirable since this can result in pressurization of the chamber and explosion. So in order to limit it, we adopted those 3 design constraints, and these are the maximum flow, mass flow through the propellant core of 1,900 kilograms per second meter squared, a minimum port to throat area ratio of 2, and a maximum motor length to diameter ratio of 12. The port to throat area, for those who don't know, the port area is this area on the figure, and it is located on the propellant. It corresponds to the propellant core, initial propellant core. And the throat area is the smallest area of our nozzle. So I think you can pass, please. Yeah.
So now for virtual conceptual design, we are basing it around a 5-inch aluminum casing, and the KNER propellants, the potassium nitrate and erythritol propellant. For that, we did a simple internal ballistic simulation with 7 base grains. we acquired a 14.8 total propellant mass and 6.67 peak operation pressure. Because of the characteristics of the casing and the nozzle, we could achieve all of those design restraints that Felipe just showed. But we know, as Felipe said, the erosive burning was a pretty big design question that we had since the beginning. We knew that doing a 5-kilometer rocket with sugar propellants would be a challenge, and we probably faced those questions. For this first design, we chose to do a simple ballistic simulation with 7 equal grains. We did not change the core diameter in any of the grains to optimize erosive burning or somewhat. This is an optimization step that we could take in the PDR or CDR phase. You can pass the slides now. For that, we also coupled our ballistic simulation with a simple 1D trajectory script so that we could have a quick estimation of how the rocket would develop. We had an estimation of 27 kilograms of rocket structure without the motor. We did some basic estimation of the motor dry mass, and we had the propellant mass already. So we could do this kind of simulation with calculating Mach, calculating acceleration, and the apogee. Something that will be really noticeable is the difference in maximum acceleration between the designs. This design is using erythritol sugar as a fuel. It has a lower burn rate than the other analyzed propellants, so we could have a higher burning time and a lower maximum thrust. Would facilitate the aerostructures projects as a whole, and that's a really good design point for this conceptual design. We can move to the next one. So for this conceptual design A, we chose to do stainless steel nozzle with a graphite insert, mainly because we would want to have in the design A and design B 2 different nozzle architectures. This one was chosen to have graphite insert because of the higher burn time is about 5 seconds, so it's almost double the burn time of the design B, and that might lead to a need of graphite as a throat insert because of these more favorable thermal properties. It's as stated in the slide, it is a relatively well-documented design. It is used by some teams. I think even one Brazilian team has used this before. But it has a cone that's graphite brittle, and none of the teams have in the cooperation have worked with graphite to this date. Can go to the next slide.
So for the conceptual design A of the propellant composition, like Igor said, we will use KNR, that will be a 6535 of potassium nitrate with erythritol. This composition have some features, né? It performs like specific propulsion 138.5 seconds. The density is 1820 kilo per cubic meter, and at the back flame temperature of 1608 kelvins. The pros of this composition is that don't caramelize when heated, and this is the and the propellant absorbs almost no moisture from the air, and this is having a slow burn rate, like Felipe said, we has less prone to erosivity. But like that, it's not well widely used here in Brazil and abroad. We have a little cone with lack in knowledge. The next. Like Igor said too, we will use the Bates geometry because it's very easy to manufacture and widely used with almost everyone using this configuration and have good documentation in a good performance. So it will be easy to scale up if we need to change things in the motor. And the only con is that don't have a perfect neutral burn area. The next.
So an inhibitor is simple a layer of heat-resistant material that is bounded to one or more propellant grain surface. In order to do that, we choose cellulose because it is cheap, widely used, and also is available. It's true that there is not the best flame resistant when compared to other inhibitors material, but this is something isn't something that we can handle. Can you go forward, please?
So as I said before in the documentation roadmap, one of the things that we would propose today is the structural architecture as a whole. We've analyzed some different structural architecture, mainly the so-called standard one, that is this one that is shown in the figure, the flanged motor and a threaded motor, where both the bulkheads and the nozzle will be threaded into the casing. We've decided to go with this standard configuration that in this figure I think is based on a Naka motor with a casing, one bulkhead, one nozzle, and an optional nozzle retainer ring. Because this architecture is really validated by international and national rocket teams, and we needed a really sturdy, trusty design for these components. The downside of this configuration is that it has screws on shear that could cause is an easier mode of failure than screws in tension that would be in graphite in the flanged motor, but and it has screws on the sides that could be a problem for the integration of further structures. But we analyzed that both those things are manageable, and the pros overcome the cons in this state. We can move on.
So the lowest temperature allowable for aluminum is 250 Celsius degrees. So to prevent the motor case achieve this temperature, we use a thermal liner, which is ablative material. And for this one, we choose EPDMs. EPDM is basically a rubber which is fire resistant, thermal resistant, and widely used by teams here in Brazil and international. One example of that is the Space Shuttle boosters used EPDM. And of course, there is widely available for us, and this is a good point to choose that. One cons is that it can be difficult to bond, but this is nothing that we can have to worry about it, since there is a special glue to bond this. Can you go forward, please? So in order to estimate a thickness of thermal layer of 3 millimeters for 3 millimeters of aluminum case, we run 12 different simulations in Thermcas. Thermcas is a software provided by Richard Naka. So having the temperature on the external case, we fit a polynomial regression to get a curve which we can estimate the most promising thickness for a given temperature. So you can see the result in the graph on the right-hand side. And so estimating 50 Celsius degrees, we got more or less 1.5 millimeters of thermal layer or EPDM layer. So this match with the results provided by Thermcas. Can you go forward, please?
Now let's talk about the best design, the chosen design. And this is the 5.5-inch architecture. And we used 6061 T6 aluminum casing. It is a pretty widely used, widely available casing. And with a 5.5-inch external diameter, we used KN sorbitol, more known as KNSP propellant. And it is pretty well documented also. Later on, Christopher will talk about more. 7 base grain segments. We maintain the number of grains in order to not put our LD higher, the length to diameter ratio that we talked previously. And we have a 5.5 megapascal operating pressure. And this is an O-class solid rocket motor. Can pass. So here we have a preliminary trajectory. It is the same kind of style that you saw backwards in the presentation. In the way that we have a height estimation and we have a velocity and acceleration estimation. In this case, the apogee is around 5,200 meters. We do reach supersonic flight in contrast with the last design. Yes, we do reach supersonic flight. And we have 12.62 Gs of maximum acceleration. So it is quite a lot closer from the 16 G maximum value that we stipulated earlier. But it is not very near, so it is not a point that will bring any worries regarding this aspect. We also have 32.4 seconds until the apogee and around 3.5 seconds of burn time. So you can pass the slide. Regarding the nozzle design, we stuck with a simple stainless steel nozzle without the graphite insert. In this case, it is a conical nozzle, but it is not. Has not been decided yet if it will be a bell nozzle, although we have discussed the main advantages and disadvantages. And this can be seen, as Igor said, as an optimization step and not essential step right now for the SDR. And stainless steel was chosen because of its ease of, it's pretty available. It has a pretty good operating temperature of around 1,150 Kelvin. It has pretty easy assembly and integration. It is just one part in contrast with the graphite insert, which has 2 parts. It is pretty cheap to manufacture. It is easy to assemble, and it is extremely well documented. And stainless steel also has a pretty high tensile strength, so it has good mechanical properties and it's not brittle. The main con of this design is the loss in heat resistance when compared to the graphite, and that stainless steel is a lot heavier than graphite. I think it is probably 6 or 7 times heavier than graphite. You can pass the design. So, Christopher?
So for the concept design B of the propellant composition, like said, we use a mixture of 65 and 35 of potassium nitrate and sorbitol. They have the properties. It's almost like the KNR, but we have so many more acknowledgement about this sorbitol. We use this like the best design, and have same property like don't caramelize and heat, and it's widely used. The only cons it's the he have a burn rate it's higher than the KNR, so he have a negative property like flushing that it is we erodes the end of the grain, the last grain. So it's a cons we have to consider. The next. For the geometry, we use the same, but the only thing will change it because the diameter of the motor will change. So this is a little bigger, larger than the first one.
So I already mentioned why we use cellulose, and basically we decided to work with in both design because it's very available when compared to other materials, and we believe it will complete the task. So please go forward.
Once again, we decided to stay with the standard as structure without doing anything different to the baseline architecture. So can go on.
So since Minerva rockets already have a row of EPDM and it is a very good material for the task, we decided to choose EPDM for both design. Please go forward again. This is basically the same simulation that I mentioned before, so you can go forward too.
So yeah, now to do a simple comparison between both the proposals. The main difference between both of them is the propellant. One uses erythritol, another one uses sorbitol, and this decision dictates some of the design showed to you. Mainly the casing diameter. For the sorbitol one, we needed a larger casing because of the 5.5 inches, because of the erosive burning issues. If we wanted to do it in the 5 inches, we would have a lot of problems due to erosive burning, and we need a heavy optimization in the next phases. So we had to increase the diameter so we could make it equal, relatively equal to the erythritol one with 5 inches. The one with erythritol seems to be really effective, but the thing is, it is a propellant that was not well tested by teams in Brazil. Especially the teams in the cooperation have little to no experience with the propellant, and doing something in this magnitude could be a high risk. But it is a really promising proposal, and we decided to include it in the slide. The KNSB propellant is widely used here, especially in Brazil, especially for large motors. I think most of the 3 kilometers solid rocket motors by Brazilian rocketry teams was made with KNSB. And we could, in both of them, do a little tweaking in the core geometry as we go along the motor, so that we could increase our total thrust or decrease the effects of erosive burning in the next design phases. Felipe, do you want to add anything?
You kind of summarized pretty well what the difference between the concepts are, and we have like the main aspects that concept A has a lower propellant rate. It is easier to control the erosive burning. It is more suitable for a high length motor, hence the diminished diameter. It has a higher cost effectiveness because of the reduced diameter of the architecture. It is lighter than concept B, It has a 70% less vehicle max acceleration, sorry. So instead of having like 12.62 Gs, we have 7.37, if I recall correctly. And none of the teams, the con is that none of the teams participating in the cooperation have previous experience with this propellant in particular. I think the concept B, you will also explain pretty well. It is based on the KNSP, which is very well documented and very pretty widely used. It has 13% more total impulse. We have a 5.5 outer diameter, hence the larger propellant web thickness, and this would result in a larger burn time, but actually we have a shorter thrust time because of the burn rate differences between the propellant. We have more vehicle acceleration, and we have more challenging approach. We have a more challenging approach when dealing with the erosive burning issues. So I think this is a pretty good summary. Do you guys want to add something? Christopher, Andres, and Igor?
I'm good.
Me too.
Final regards.
I'm good. So the final slide.
Thank you guys. Thank you guys so much. The work is impressive. Congratulations to all members of the propulsion system. The work is unbelievable. I think this is a live classroom for a lot of people that is in this live stream, and for future generations that will access this video on YouTube. Congratulations, nice. Okay, now I will pass the word firstly for Alexandre Goulart. He has some questions. Go, Alexandre.
Well, so first, thank you for your presentation and congratulations. Really extensive and very good quality work and material you're bringing here. So let's start with my first question. Just, I think maybe I just lost something right at the beginning, but about the pressure relief system, is this going to be implemented, or I just didn't hear well, just what's exactly about it?
So the pressure relief system is actually an open topic at the moment, but it's basically to try to instigate the teams to find a fail-safe mode of the motor. We had some suggestions like doing calculating so that a different number of screws in the bulkhead and the nozzle, so that when we reach a certain overpressurization level, the nozzle would eject and have a greater area and avoid the casing explosion. That would be a way to have this fail-safe mode. But it's an open question. We haven't really talked much about that.
Okay, yeah, and that's something that can be implemented later. So yeah, okay, good, thank you. And another question is, what are the burn times for each concept?
The burn times, I can check here now, just 1 second. The burn time for the concept A is exactly 5.20, no, sorry. So 5.41 seconds of thrust specifically, and a neutral burn profile. And the concept B, we have 3.45 seconds of thrust and also a neutral burn profile.
Okay, and associated with this burn time, what are the thickness of each grain? like the port radius minus the external radius.
So the thickness for the concept A is 30.5 millimeters, and the thickness for concept B is 30 millimeters.
Okay, so they're very similar. Okay, that's especially a concern considering the mode, right? And also, I would just also like to comment about the inhibitor. In fact, the cardboard or let's say paper inhibitor is not cardboard, but you understand what I mean. Is reasonable. It's possible to use, but specifically my suggestion would be to try to invest more. Maybe consider more. How do I say, more reliable choices, but also I'm shooting this question to you because I think it has a lot to do with the manufacturing method, the molding method of the grain. So for example, if we're going to mold it with the inhibitor or glue the inhibitor after, well, it's up to you, but it's something that's very important to be really, really reliable. My experience specifically, in the past, I have had problems with paper-based inhibitors, and what happens is that you get a much bigger burning area, hence much higher pressure. So much higher pressure, much higher thrust and everything. So just a suggestion that I believe that's something that can be changed later. Also, it's not doesn't have to be written in rocks right now. And also about now really a question, but about the thermal liner, how are you thinking about to fix it inside the combustion chamber? The interfaces, are going to use some silicone-based glue, let's say, or something like that?
So yeah, we haven't touched in this specific topic, but in the renderings we've used it. Something I forgot to say. The renders are just a really conceptual design. We took an existing motor, the Minerva Rocket's 3 kilometer motor, and just scaled it up to fit the proportions. But we haven't defined the thickness of the bulkheads, the number of screws, those things yet.
Of course. Okay.
But I think if we move to the concept B slide, there is a rendering where we could see what is done to fixate the thermal liner. Can we move the slide, please?
No,
the concept,
one more.
No, it's this one. You can see that there are. It's really hard to see, but there are two O-ring grooves, and one of those grooves is a O-ring that seals directly into the thermal protection. This might be a kind of overkill method. We are still experimenting with this one in the Minerva Rockets team, but what I was thinking about is if we consider this one an overkill, we could just have a section of aluminum that gets that fits over the thermal protection, doing kind of a sandwich between the casing, the thermal protection, and one part of the bulkhead, and in the nozzle end, one part of the nozzle. Just having this section being locked down in position by this
Okay, I see what I mean. So I have two comments concerning this. The first one is that one of the interfaces I'm mostly worried about is the longitudinal one, because you're not going to buy a tube of PDM, you're going to buy a sheet of PDM. And do you have any comment specifically to the longitudinal?
Yeah, for the longitudinal one, there is a specific glue for EPDM that is used for roof liners and such. And we're thinking about using this one with probably aluminum tape in the outside.
Okay,
or
great.
something like that.
And okay, that's great. And the other comment is about the O-rings. Usually to get the O-rings to seal properly, you have to have really tight geometric constraints. And since it's a rubber sheet and it's also flexible, I believe it's not very, I don't feel very comfortable with using a O-ring with EPDM. I believe the O-ring to the ceiling with the O-ring should be where you can get really good geometric tolerances. That would be between metallic parts, and maybe it would get better results with a most general interface there. Also, because if you're going to use two O-rings, you can get more more reliable seal, really, because usually use silicon-based O-rings, and usually we are operating then at their limit or even a little more. So I'm getting a little concerned about this interface.
Yeah, I see what you mean. That is something that we're still experimenting with. Probably in the cooperation motor, we're gonna have both O-rings sealed with the casing, and some protrusion on the bulkhead just to have the lock it in place.
So you mean the protrusion, the difference in diameter, right?
Yeah, the different diameter to do a sandwich just with aluminum, the thermal protection and the casing, the bulkhead, thermal protection and casing.
Well, okay. I think that can be discussed further later, but just to show, I think it's a concern. But that's fine. That's possible. Everything. I believe Yamato has something to say.
Okay, thanks, Alexandre. Thank you, Felipe and Igor, for the presentation. Very good introduction and talk about the roadmap. It was very, very clear, and congratulations for the entire propulsion team as well. Well, for one thing that I missed on both design was some information about the average thrust, total impulse, and a table or a graph with the burn time and pressure and thrust. Sometimes it's good to see what is happening on time. And also, just some questions about the design A. You said it's not the best one, but just some comments. First, about the snap rings. Find some snap rings here in Brazil for these dimensions. Maybe it's kind of difficult, and maybe only one is not enough. Maybe two or more. And when we are using the snap ring, we have to do a cut inside of the tube. So usually the depth of this cut is like something about 2 to 4 millimeters, and it can be affect the casing structure. So for large motors, large diameter motors can be a problem, and to machine it using a CNC or conventional milling tools maybe is very difficult because of the length of the motor. Something about 1 meter or more, I guess, is the motor length, and it may be difficult to machine. But talking more about the Conceptual B, that you and I think also is the best design and best option here, as you guys have more experience working with the propellant. About now a question about the tube sizing, diameter, and material. Did you guys find some supplier for this tube already? Because many of aluminum tubes that are made down here in Brazil, they are made for specific projects, and they sell the remaining parts for the average public. So did you guys find this specific tube?
We found a supplier in São Paulo, and we have already checked the prices and the availability. In particular, for the 5.5 inch, there might be a slight modification in the outer diameter and the thickness of the tube, but it won't affect much the overall performance of or mass of the proposed design. And we already have the costs and the proper alloy, and it is not the architectural aluminum alloy that is commonly sold in some stores here in Brazil.
Yeah, there is a slight modification because it's not exactly 5.5 inch. It's a schedule standard tube, 5 inches that is kind of 5.5, but not really. And about the snap ring concern, I think I didn't explain myself right. It is not a machine is a retaining ring, a snap ring. If you see in the in the other presentation, there's a better render that shows the retaining ring. What I meant was just aluminum ring that was machined so that it could take screws and lock the nozzle into place, so that we didn't have to make a nozzle so large to fit the rings, the screws, and increase the mass a whole lot because of that.
Oh, okay, great. Great you guys already find the tube as well, because it happens a lot here. Sometimes you buy like 6 meter of some tube, and a month or 2 months later, when you are trying to buy it again, the supplier don't have it because it was not made it. So thanks for this. And other question is about the ISP. For the second one, you say that is around 130 something seconds. Is that right? So is this value a theoretical one, or did you make? Or are you guys considering some losses like burning loss, nozzle loss, combustion efficiency?
Yes. So the simulations we did, we considered the boundary layer losses and two-phase losses, combustion losses, and some other mainly pretty well-known losses. And the specific impulse for the second design is 125 seconds, and for the first design is 129 seconds. This is due mainly to the higher chamber pressure that the smaller tube can reach, and concerns regarding the erosive burning. So we can't have a very high chamber pressure on the second conceptual design, the chosen design, because it is limited by some mass flow constraints.
Okay, thank you, Felipe. That's great. Maybe it's great also to have take some data from. I think Minerva have done a lot of static fire tests using their KNSB motor. So maybe it's great to have this experimental data about the ISP to do some adjustments on the efficiency as well, because sometimes when we test the motor on the test bench, the ISP is like 10 to 20% lower, and maybe this is good to improve the performance on the flight as well. Well, I think is that for my end. Thank you very much, and again, congratulations for the work.
Thank you, Amato. That's a great suggestion about the experimental data. Thank you for the suggestion.
Thank you, guys. Vitor Capacia, do you have any questions or comments?
Yeah, Calvin. Just I'll not go too deep on like Yamato and Alexandre did. Just a small comment. I think the main challenge on these cooperative projects is the scheduling and maybe manufacturing assembly after you guys have to put it all together after parts manufacturing. I really like the roadmap. It was it's a really nice plan to attack the scheduling problem. I think maybe the challenge would be to associate the roadmap with the schedule and keep up with that. But I really enjoyed the presentation, and congratulations everyone. Thanks, Calvin.
Thank you, Victor. Isabella, are you on? Do you have any questions or comments?
I have no comments.
Okay, thank you, Isabella. Matheus Cruz? I think he is not here, so Matheus Belo?
No questions.
Okay, thank you, Matheus. I have a few number of questions. The first one is about the pressure. The pressure in the first concept design is about 970 psi. That's more or less 6 megapascal. And the second one is 760 psi. I strongly recommend the second design, and just this recommendation is to make it lower, not 760, but maybe 550 psi, 600 psi. That's more or less 4 megapascal. It's going to be safer. Like I said for you guys in the first meeting, the internal meeting, the safety is our value number one. So I think more than 650 psi is something too great, a great number. It's too high. I don't like something more than 600 psi. So I strongly recommend for a redesign with a lower pressure. Okay, and I have a question. It's not a question, but it's something like Yamato said about the specific impulse. We test a lot of solid rocket motors in the past. I think more than 50 to 100 motors that you already test in our lives. And I think 130 seconds or 140 seconds for a project is something that we will feel just during the 2020 LASC when the rocket stops by 4,500 meters. So I think you have to consider the experimental data. So I think maybe 120, something like that. You really need to go a little bit in depth during the preliminary design review with the experimental data available on papers, or for example, Minerva already has tests.
Database?
So, yes, database that can be used for this intention. I really prefer the concept design B because I think KNER 83 tall, I don't know how to say that in English, but it's something new for everyone, and working in a challenge for 5 kilometers, I think that's best to work with something that part of the teams already know. So I strongly recommend the concept design B with sorbitol. Okay.
Great, Calvin. Just a little correction. I think I have, I don't know if I have misspoken something, but the specific impulse of the first design was 129, and the specific impulse of the second design was 124. So it is not the theoretical value of 100 and close to 140 that the propellant has when it reaches like combustion at 1000 psi or that value that we put in the propellant composition was a value that we used on the decision matrices in order to compare the propellant. So sorry for not clarifying this before.
Okay, thank you.
And
Now
just
it's
just
okay,
a
go
fast
ahead,
question.
Igor.
Yeah, fast question. What's the thickness of the tube you're using?
Both of them are a quarter inch, 6.35 millimeters.
6.35. Wow, that's a thick
Yeah.
wall.
Yeah.
Okay.
Because 5 inches or larger, we could just find the in this thickness. And just a quick point, the whenever has tested and is testing 5.5 MPa KNSB motor, and the last static fire data shows an ESP of 123, so it's pretty close to the 124 that was estimated in the ballistic simulation for the concept B.
Okay, nice, Igor. Nice data. It's going to help a lot you guys in the preliminary design review. Just my last comment is about the inhibitor. I worked with cardboard, paper, like you showed on the presentation. One time before, I think it was 2,000 Newton of thrust solid rocket motor, and I don't like a lot the cardboard paper, something like that, because they have like a resin on the surface, and this resin will make the bond between the propellant and the inhibitor a little bit difficult. So maybe you, like Alexandre said, maybe you can go and do some rehearsal and research, sorry, in this part of your motor, because the cardboard and things like that is not something easier to have. I have one example that the flux of gases pass between the external diameter of the gram and the inhibitor, because of the bond was not too good. So it's just a suggestion. You can go in that during your preliminary design. Okay, I think in this one it's something that everyone in the evaluation committee said the concept design B is the best, like you guys. So I think we have something aligned here, so we can go on for the next subsystem. I would like to congratulate everyone in the propulsion system. Congratulations, Igor Novis and Felipe Bogart. Their work was impressive.
Calvin, just a little question before we move on. What would you and Goulart suggest about the inhibitor? Use an epoxy-based one, or
yes,
something like that?
Fiberglass.
Okay.
Yeah, there are more options, but fiberglass is a good starting point.
Okay, nice. Congratulations, guys. Let's go to the next system. The next system will be the Avionics system. I will pass the word to Monish Mathur from India, Dual Rocketeers, and João Victor Curado Fleury. Good night, guys. Thank you for having you tonight with us.
Thank you, Calvin. It's a pleasure.
Good evening, everyone. Thank you, Calvin, for inviting us on this presentation. So today we are presenting the Avionics System Design Review. for the LASC Technical Cooperation Report. The next slide, please. So in today's presentation, the outline, the first, we'll present the task assigned to the avionics subsystem in order to reach the aim of this cooperation project. These tasks are set the expectation to be delivered from our subsystem. After that, we will present the avionics architecture that the team designed. The team was further divided into 3 sections in order to ease the workload and achieve the mission requirement smoothly. The 3 subsections in which the team is divided are video recording, mainboard, and telemetry. Following that, the 3 subsections will be presenting their proposals they researched during this phase. The presenter teams for today's presentation are Monish and Joao as PMO and Vice PMO, and the additional presentation here are Eliosa and Olavo, who will be presenting the video recording section, Rodrigo, Larissa, and Lucas, who are responsible for the mainboard section. Next slide, please. So there are 4 tasks assigned to the avionics subsystems. The first one is that the subsystem will carry the 4 altimeters in which we have to identify the apogee and trigger the recovery system. In those 4 altimeters, it is suggested that 2 are from the PION labs and 2 are the commercial off-the-shelf systems, which will be decided by the team. A second task for our subsystem will be to perform the real telemetry and the flight data capture. The data should be transmitted to the ground station through which the team can observe the flight path and the flight data during the mission. The third task assigned to us was to provide the GPS location of the rocket for the 3 hours so that the rocket can be safely recovered after the landing on ground. And the 4th task, which is innovative and a new task for us as well, is to provide a live stream 360-degree video of the flight launch and the trajectory of the whole mission. Calvin, next slide, please. Thanks. So here is the avionics architecture and the interfaces. This system architecture will allow us to define the required performance from each section. We created a dotted box here which segregates the task for each section. The main board will work on the flight path sensor, which will feed the data to the microprocessor. The microprocessor will be responsible for recovery trigger system and also will gather the data from different sensors and will send it to the telemetry section. Similar task in the video section as well, where the live stream of the video will be captured and sent to telemetry section for the transmission on ground. After that, the main work for ground station would be to the main work for the telemetry section would be to transmit this data through the antennas to ground station, and the ground station will then receive the data, and first one will be to stream the live video via YouTube as suggested by LASC, and the second to print the information which will be provided by the sensor. So next, we will be presenting the video recording section proposal.
For our video recording challenge, we have to transmit a 360 degrees video live on YouTube from the moment of ignition to its apogee.
Olavo, are you in this meeting?
He's trying to
Hello?
talk, but I think, yes, now we can hear.
Hello, you can hear me?
Start over,
sorry.
please.
So based on that challenge, we have developed 8 possible scenarios, and we're going to present you the 2 with the best cost benefit today. You can pass to the next slide, please. For an image with an angle greater than 120 degrees, we obtain a spherical shot, making it necessary to planify the image. And for a complete 360-degree view, at least 2 lenses are required. In these cases, it will be necessary to unite the images in a process we call stitching. And for this, it has to go through a software.
Due to the level of complexity and the time spent in the process, doing it on ground base will make the live transmission impossible. Therefore, we decided to look for solutions already on the market. All the solutions we brought to this presentation will be placed inside the rocket, which requires a transparent part in the fuselage.
Also, because of the high image quality, the transmission must be compatible, and this eliminates the possibility of an analog transmission, since it is limited to the 480p. And so we talked about the Wi-Fi. However, its protocols divides the message into several packages, and if an error occurs, the entire message would be lost. So we opted for the digital transmission that, despite needing a booster and antennas to have the range we need, and it manages to send the message with the quality and speed required for this challenge. Also, the video link module can be used as a redundancy for the telemetry system.
You can switch the slide, please. So we selected 2 possible dispositions for this project. The first option brings us a 360 image that will accompany the horizon line, and the other will have a greater attention in the interior of the rocket, which would make it possible to film the parachute opening. As the image suffers a distortion at the edges caused by the lenses constructions, to obtain a quality video that is possible to view well, it is necessary that the camera films in 1080p or more, so at least full HD. You can change again, please. For this proposal, these camera's models were chosen. The Kodak Spix Pro Orbit 360 degrees for proposal A, and the camera 360 degrees VR Full HD for proposal B.
You can change the slide once more. Well, the main difference between the proposals is the image type and the video quality. The proposal A offers us a better image, but the proposal B is less expensive as well. So you can change the slide again, please. For a better understanding of our system, we built this schematic. Our trajectory starts with the camera that will register the video and send it to the video link, which is responsible for transmitting the digital signal that will be received from the camera with an HDMI connection. The signal sent from the video link passes through a booster, which will amplify linearly the signal and pass it to the antenna. We need 2 antennas in this project, one omnidirectional, which will transmit our signal while the rocket isn't too high yet. And when it reaches a certain point, the antenna will be changed to a directional one, so we can receive a stronger signal.
For the ground station, we have a receiving antenna for each one embedded on the rocket. We also have a receiving video link that will be connected to a capture board responsible to convert the HDMI jack into a USB, so we can connect it to a computer, identifying it as a webcam, so we can be transmitted on YouTube and everyone can appreciate our work live. And now we're going to present about our main board project.
So the main board section is basically from where the electronics inside the rockets will be controlled. This section is expected to deliver the basic flight path data from different types of sensors like GPS, barometers, thermometers, and accelerometers. This section is also responsible for designing the trigger system for the recovery subsection. As shown by the picture on the screen, all data will be sent to the main microprocessor, which will process and store the data in the main board itself in components like SD cards and flash memory chips for post-flight analysis. The crucial data will be also sent from the transmitter inside the rocket to the ground station where the telemetry team can process it and store it as a backup. Now we will present more on the telemetry section.
Telemetry starts your research thinking in a way to get a long-range and trustworthy connection. Among the options researched, low-ray seems the best option to perform this mission due to robust protocol and the previous experience of some members. Can you please change the slide? Yes, this picture is a very good illustration to explain the LoRa capacities and his coverage. Once more again. Please change the slide. Yes. LoRa can be used with any microcontroller that supports ESPI or UART communication. As LoRa provides a point-to-point communication, we won't depend on any third-party service for its operation. There are no fees to pay, and there is no restriction on signal coverage. In addition, the LoRa protocol natively implements a forward error connection, a mechanism that makes the message more robust even with interfaces. So the following proposals are based on LoRa modulation operated in 950 megahertz. The radio will transmit, the radio transmitter will be welded on the board, collecting all the sensors reading and send it to the ground station. On the ground station, we will have a receiver mounted with another microcontroller that will interpret the package and show it on a PC screen. And now we will present the main board components.
I will talk about the components we intend to use, but without entering into very technical aspects. The microcontroller is the brain of the system. It reads the sensors, processes the data, and sends commands to the recovery system. We believe ESP32 is a nice option, mainly because of its high performance. It is almost 12 times faster than Arduino Uno, which is a microcontroller commonly used for simple applications. To measure the altitude, which is essential for event detection during the flight, we will use a barometer. The two options shown are inexpensive and reliable, differing in accuracy. Another method of identifying the rocket's liftoff involves acceleration. We can measure this using this accelerometer, capable of measuring acceleration in 3 axes with a full scale of 16G. Furthermore, it can measure angular velocity around 3 axes and magnetic field intensity in 3 axes also. Can you please change? Thanks. To map the flight and mainly to help finding the rocket after landing, we intend to use the GPS. It's small, easy to use, inexpensive, and can acquire latitude, longitude, altitude, and horizontal speed. To store the flight data, we intend to use a micro SD card, in which we can create many text files with various data. Along with that, we can use a flash memory chip, which is more reliable against vibration and acceleration, and can also store essential data during flight. And lastly, I will present 2 ideas that are in study. And the first one consists in, no, it's that one, another slide. It's the same as the last one. Can you please return a slide? Yes, this one, thanks. The first one consists in utilizing a temperature sensor near the motor, so it can detect the rocket's liftoff based on the motor temperature. The second one involves a sensor that indicates when it passes by a magnet. The idea is to fix the sensor in the fuselage and fix a magnet in the launch rail, in a position that crosses with the position of the sensor. And now we will present the telemetry modules.
Regarding the LoRa modules proposed, they are based on the same IC, XX1272, and the first one is the 822, and it will be connected with the microcontroller by the USB protocols. And the second model is the E32, and it has an additional IC that makes the coding easier, taking care of some parameters, but it's decreased the telemetry flexibility. Could you please change the slide? Yes. The system will demand a fiberglass part on the rocket to allow the signal to radiate, and omnidirectional antennas were chosen because it spreads the signal all around as being a better solution for moving objects. Just to finish, some members already have worked with similar components that were presented above, and they got an incredible mark of 16 kilometers, transmitting around 50 bytes of information per second. Now Larissa will present the design assembly.
Now talking about the main board, the design assembly we have respecting some specifications, like not exceeding 10 by 10 centimeters and using 2 layers to lower the cost and facilitating the manufacturing. Here we have an image that is useful to compare the size of the components with the total area available. This board is the image have 10 by 10 centimeters. That is our estimative. And the components such as voltage regulators, LED, and resistors will be SMD to save space. You can change the slide, please. Thank you. About the operation in the both concepts, we have the measure of altitude will be made use the barometer, convert the current air pressure to the rocket's altitude. To trigger the recovery system, the accelerometer will be used. So the microprocessor software will be engineered in a way to check for the launch data and the altimeter data to indicate the falling of the rocket. During the flight, all data from sensors will be stored in the micro SD card for analysis later. You can change, please. So about the first proposal, we focus in using several different sensors and a storage unit to log all the readings from the previously mentioned sensors. Here we have a component list. It will include a microprocessor, the SP32, which will work as the main computing unit to coordinate however data will be processed and stored. We also have some of the sensors already mentioned. You can change. Now on the second proposal, this concept is very similar to concept A. The only change in operations comes with the secondary storage device in form of flash memory chip and the change of the barometer. As we can see in the component list, now we have the BMP 388 as a barometer in place of the BMP 208. The other components will be the same. You can change the slides, please. Yes. As we can see, the proposals are very similar, so we will highlight their difference. About the barometer, the BMP 388 from the second concept offer the same functionality as the first concept, but with more reliability and precision. The SD card is prone to problems to vibrations and loose fitting. So the second concept proposed the use of a flash memory chip in addition to the SD card to store information. This solving most of the reliability problems with the SD card, but offering less storage space. So this option, the flash memory chip, would be used as a backup storage solution for the most essential data. And you can pass. We finish here. This is our Avionics system. Thank you for your attention, and any questions, we are available.
Thank you, guys. Thank you for all the effort. The presentation was great. I think the requirement for the 360 degrees video is something never seen in Latin America. It's something new. I think if in 1 year from now we launch the 5-kilometer rocket with this 360-degree camera working and live streaming the launch via YouTube, I think that we reached something else. I think the complexity of the system is huge. I think you guys are doing a good progress. I think that for a concept design, all the system presented is something good. Personally, I don't have any comment. Just I want to congratulate each of you. It's a nice project. Now I will pass the word to Gabriel Yamato.
Yes, thanks, Calvin. Thank you for the entire team for this presentation. It was really good. As Calvin said, there is a very challenging requirements here. That is great because push ourselves to something new, something with more innovation. And just a quick question. Did you guys made some link budget analysis between the receiver and the transceiver on the telemetry system?
In fact, we already started doing that, but we passed this task for the next phase. The content presented here tonight was based on the previous experience of our members.
Oh, great, João. Thank you. And just a comment, maybe it's good to have on the future, on the development process. Of course, not for today. It's many details, but there is some simulations that can be done with some simulation software or even by hand using some coding. You can calculate the budgeting performance and maybe also take care of the positioning of the antennas. So usually, probably you guys be using duck antennas, like omnidirectional ones, and you can see in certain points of flight where the altitude of the rocket is different, or when we have the rocket falling down with the parachutes, maybe the rocket is spinning a little bit, or if the spinning of the rocket will not affect the link budget due to the antenna radiation pattern. And also when the rocket lands, maybe the position of its lands, of if there is terrain on it, maybe is a good approach. So do the budget analysis using some rocket altitude data and antenna positioning as well.
Thank you, Gabriel.
Thank you. Yeah, that is from my side. Alexandre.
Well, I believe you covered everything I was thinking about. So maybe who's the next that would like to talk? Who would like to ask questions?
Thank you, Alexandre. Let me ask if Mateus Cruz and Mateus Bello, if they have any questions.
No questions.
Okay, thank you, guys. João, do you like to talk?
Yes.
Thank you.
Hello, everyone. I'm just checking here if I did everything right on the stream, because I'm answering you and controlling the stream both at the same time. So some things could go wrong, but everything is okay. I have some questions for you regarding some of the diagrams you proposed here. I see that there's a diagram that you have something like a battery on the center. And I'd like to ask you if you are planning on having just a single battery or like a lot of different batteries for each subsystem, let's say it like this, because I think it's better to have like one battery for each system to keep them isolated in case of failures and etc. But the overall thing that you proposed here on the beginning was okay, really good, and the work is really awesome. The barometer chosen is like the best option that we have available here in Brazil. There are some other sensors, but you chose wisely, and the BMP is widely used and have a lot of information around, so that's a very good one. I'd say that the BMP 388 that you chose for the another proposal is has kind of a better precision, so you can it's wise to choose this one, but it's less available. So I don't know, maybe you guys can see about that. I really don't recommend using the MPU 9250 because it's discontinued and it's on its end of life. It has an end of life requirement from the manufacturer. The InvenSense, the manufacturer for the MPU 9250, has discontinued the whole MPU lineup. I know that this is a very common IMU to find in the market, but they really discontinued because it's kind of bad and has some problems that they discovered in the middle of the selling of the product. So I really recommend you to maybe pick another one, maybe the Bosch ones. They are really good. The BNO 55, I think, BNO 80, BNO 88. I don't think the part number right, but those others are really good. They drift less and some other things like that. And another suggestion I have is to not use the motion processor that you have inside the MPU 9250 if you choose to use the MPU 9250, because they use some kind of mathematical equations to like find out the positioning, like the pitch, yaw, and roll of the sensor, that are not good for working with rockets, because they're good for working with things that are on the ground, like robots and maybe something like drones, but not with rockets that are constantly accelerating towards the sky. They generally throw some errors. And that's what I have to say about the IMU. And about the two concepts, I think the flash memory chip, it's really good to store things during flight, and I think it would be a great challenge, and it's like a great challenge to work with the memory module, because it's very different from how we work with the SD card. So, and it's like harder to work with, but you guys are going to learn a lot, and it's a lot better for the flight. So the majority of the altimeters and other systems, they store the flight data in flash while in flight, and when they land, they detect landing, and then they transfer this thing from the flash memory to the SD card, so you can read and work on it later. I have one question for you about, my first question was about the battery, and the second question is about which digital modes do you think is best for the video transmission? I think I heard something about ADB, or the one that they use on digital TV, but I really couldn't grasp what we were proposing. And this other question, and the LoRa is wisely chosen. I think LoRa will work great for the rocket and for this proposal. I just think that the antennas are going to be something that you can focus later, because a direction antenna, and like Yamato said, can have a better efficiency than a duck antenna or omnidirectional antenna. And watch out for the 4K options on the camera models, because this camera is 4K or 1080p, provides a lot of data that you have to move around places. So be careful with that. But I really liked everything that you did here. The board as well. The board is very good, and I think that maybe just try to think more about the connections here, because the connections are being made with pin headers, and during flight, the vibrations could do something to those pin headers. So maybe solder them, the pin header directly without a female header, or some other way, because as we are building rockets, the vibration is something that can like disconnect some devices while you are flying. So it is good to pay attention to these smaller details. And yeah, it's just these two questions that I have for you about what you thought about battery options, and what is the protocol that you are thinking for the digital transmission that you talked about for the live stream.
Thank you, Joao, for so much information. And regarding the battery positioning, so for now we just proposed like the single battery in the main PCB. But yes, we are thinking for a backup battery option. We just have to talk with the structures team regarding the positioning and the available space in the avionics section that they're providing. So after that, we can decide for the backup battery. But like in this design proposal, we proposed a single battery on the PCB. So we will be considering your suggestion to keep a backup battery.
Okay, thank you.
Yeah. And your second question was regarding the camera module, right?
But regarding the transmission, that you guys talked about a digital transmission, and I wanted to know if you have already like the which kind of transmission are you going to use, like which modulation. You talked about Wi-Fi, but then you talked about some like things that Wi-Fi have some problems about using Wi-Fi. So you are going with Wi-Fi, another modulation. What is the protocol that you are?
Okay. So like we actually searched for the Wi-Fi option, but it didn't went well. So actually we are like there are some suggestions in the camera module. The module itself has some transmission strategy regarding that. So we are considering that, but that research part is still ongoing, because the finite since the data is collected from the camera and the transmission link is like we need a proper transmission for the live telemetry, and that feed should not be interrupted. So we are actually finding more options to have a definitive transmission transmission antenna for the video capturing system.
Okay. One other suggestion is just for this system is for you to check what Copenhagen and Subaru did with their rockets for transmitting. They have some YouTube videos about that. They used the DVB, digital TV, digital broadcasting TV protocol, and they really did a nice job. And the rocket went like up to 2 kilometers with perfect video transmission from more than 2 or 3 cameras. So you can maybe check something around that and work with that. If we don't have any other questions from the chat here on YouTube, we We have a question from Lex Machado. How are the cameras attached to the fuselage?
Luis, do you want to answer this question?
Yeah.
So regarding the attachment part, so the thing is that as presented in the structures section, they have provided a separate slot in the in the nose cone, bottom of the nose cone, where the 360-degree cameras will be attached. So regarding the internal attachment, the structure sections are looking for a more definitive way, so that the camera module can give a fixed angle of the picture and do not rotate while when the flight starts. So that part is still ongoing, we are discussing this thing with the structures department, but the camera positioning will be the angle will be outside, but it will be below the nose cone, between the recovery and the nose cone part. There's a bulkhead between that, so that's the position for the camera.
Thank you much.
I think we also have a question for the public.
From João Stargan, so another question.
Pedro Rodriguez asked about how the cameras will be attached, will be connected with the main board. To clarify, the main board and the cameras will be like independent systems. The cameras will be placed in another part of the rocket. They will be their own transmission module, and he also be operated with the batteries with their own manufacturers. And another question is why to use the temperature sensor and not the altitude variation, then the barometer or the accelerometer to check the launch. About the temperature sensor is because it is a thing that are currently on study, and we are thinking to measure the temperature and the head of the engine to further analysis.
Thank you. And so I think after that's it for the Avionics subsystem. We can proceed now to the next subsystem, the recovery system. The recovery system is commanded by Sarah. Yep, we have right now. Is Sarah here?
Good evening, everyone.
Yes, sorry.
I am representing the recovery subsystem. I'm from Phoenix, from UFMG, and I'll be presenting now our conceptual design for recovery. Okay, please. So I will be presenting a mission concept of operations, similar to the one that Calvin presented on the beginning of the presentation, but with more specifications for the recovery. And then we'll present the conceptual designs that I'll present the operation of all the subassemblies of the small parts, how they are supposed to operate in the system, and then the conceptual designs with combinations of these subassemblies. So, so here we have the mission concept of operations, similar to, as I said, similar to the one that Kevin showed. And according to the LASC documents, the vehicle will be launched at an inclination angle of 80 degrees. And then at the apogee, it will deploy the jog chute. And in order to do that, we have decided to separate the nose cone from the fuselage, to create an open path for the parachute. And the nose cone will also serve as a bullet to pull out the drogue chute. So the drogue chute will stabilize the descent and start the acceleration without much drift. And at 500 meters above ground level, the drogue chute will deploy the main chute. And I'll explain further with more details this interface. With the main chute deployed, the vehicle will finish the deceleration to reach ground level at 10 meters per second or less and ensure the full integrity of payload and the minimal damage to the rocket structure. Pass, please. So the first subassembly that we have is the hatch opening. So in order to the parachute to be deployed, we need an open path, and there are a few ways, a few methods that we can use for that, and we have analyzed some, but we have chosen the separation of the nose cone over the lateral hatch. These were our two main options because the lateral hatch had many issues. So we have decided that the nose cone will separate, and in order to have the nose cone separation, we need an ejection mechanism, a small ejection system to actually make that ejection, that separation. And I will present then our two options for this ejection, nose cone ejection method. So next, please. Okay, here we have a illustration of how the system would be assembled in the rocket. In the nose cone, we have part of the avionics, the cameras, and the circuit to activate the ejection system. And then we will have a bulkhead, probably open bulkhead to save some weight, bolted into the nose cone, and then this gray small module for the actual ejection mechanism, and the bottom bulkhead will be bolted in the lower fuselage with regular bolts, and in the nose cone with shear pins. So the shear pins will break when the ejection system activates and create some transversal forces here, sectional forces. So next, please. So our options for the ejection deployment were, there are some options of movable pins, actuated by servos or solenoids, but they seemed very unreliable. So we have chosen to choose the ejection with expansion of gas. So this ejection works by an expanding gas in a pressurized volume that will create some forces to break the shear pins and separate the two parts of the fuselage, the nose cone, from the lower body. Here we have an illustration of how this system can be used with hot gas or with cold gas. With hot gas, usually, okay, we use black powder. It is usually used for this application. But with hot gas, it's an explosive charge that, when ignites, creates the gas expansion and ejects the nose cone. And here is how the configuration would be using the hot gas. This is a hollow cylinder, so the explosive charge would be placed in the walls, inside the walls of the cylinder. And this is interesting because it creates a very small volume. So we need a small. We will need a small amount of explosive charge. So the inferior bulkhead will be open. We'll have this will be hollow because it needs an open path for the parachute deployment. And the superior bulkhead is also hollow to save some weight requirements. And then the fixation can be by a threaded joint or maybe other options. Clark, would you like to say something? Sorry, it's just there's some noise here. I thought someone wanted to say something. Sorry. Well, using the cold gas compressed CO2, we have a cylinder with compressed CO2, and this system activates the cylinder. There is also a small explosive charge that will be activated by the electric signal and make this pin puncture the compressed CO2 cartridge, and that will create gas expansion in the pressurized volume, and will also similar to the previous one, make the nose cone separate from the fuselage. Yes, please. So this would be the assembly of the CO2 cartridges for the inside the system. Here is the nose cone with the avionics on the top part. On the bottom part, there would be the drogue and main chute, like the previous overall illustration. Here the open path for parachute deployment, and here it's a solid plate that will stop the gases from leaving this pressurized volume, will allow the compartment pressurization. Sorry. And the force generated from this pressurization will break the shear pins, and then, as said previously, separate the nose cone from the lower body. You can pass, please. So after we eject the drogue chute, will be deployed at the apogee, and then we will have the initial descent, and at 500 meters above ground level, the drogue chute will pull out the main chute. It will serve as a pilot for the main chute, because this is a safer approach to guarantee that the main chute will open quickly and with reliability, without problems. So we need a system that will allow this delay. So it's a system that can withstand all the weight of the rocket and the high inflation loads from the parachute as well, because when it opens in the apogee, there are some considerable inflation loads. So we need a system that can withstand all of these forces, but also release the drogue chute when the main chute deployment event is predefined moment comes. So, next. So we have, for to solve this problem, we have decided to use a configuration that is widely used for skydiving. It allows all the forces from the cords of the drogue chute to be loaded into one fixated point, and then they release the interface that actually releases the drogue doesn't have to withstand all of these forces. So we can separate the interface that will withstand the forces and the interface that will release the drogue chute. And that's very interesting because it's hard to find and achieve a mechanism that can withstand such high forces and still move have this change in configuration. So, well, we have decided to use it is widely used. It is very well fundamented. It's a very good system. So next. Now, to release the joke chute, this is a illustration of how the joke chute will be attached, fixated to the rocket, and this would be the separation bulkhead. So there will be a U-boat in the lower part of the separation bulkhead, where the parachute or where the joke chute can be fixated. So one of the options for this release mechanism is to use a conductive material that will heat upon activation and melt a nylon cord. Because this system, the solicitations in the release mechanism, they are very, very, very small. It's about 1% of the solicitation on the U-boat, for example. So we don't need a interface that withstands high loads for the releasing of the joke. So this is an option, and here the conductive material will heat and melt the nylon cord or line, and when it's melted, it's loose. The rest of the system will unfold as showed in the previous slide. So next. Another option for this release mechanism is to use a actual mechanical device, and we have chosen to use an option with servo motor. So this illustration, it is just to illustrate the working of this mechanism, and not quite the placement of everything on the rocket, because this is better for visualization. So this is adapted from high loads, from devices that can withstand and release high loads, very high loads used in boats and ships and these kinds of things. So we adapted to use to our purpose, to our application. Here in the first part, before the release, this half circle mechanism, this half circle lock, keeps the mechanism armed with a spring pulling everything down. And at the avionics command, the servo motor will spin, and the spring will pull everything down and unhook the line, releasing also the joke chute. Next, please. So after the main chute is deployed, we will have a configuration of the nose cone. We will have many different parts. So we have the joke chute and the main chute and the nose cone and the lower body. So how we assemble this configuration during the descent is very important too. So can you pass for the next, please? So our most, well, the options that were more fit for our application would be to link the parachutes in a parallel manner or in a serial manner. So this is used in order to minimize, reduce the size of the main parachute. After the main parachute opens, we can make a configuration, link everything in the configuration, that the drag coefficient, the drag from the drogue is still used. It's still active in the system. So we can make this kind of architecture and configuration to use both the parachutes after the deployment of the main parachute, and we can minimize the size of the main parachute and reduce weight, reduce space occupied, and all that. So one of our options is to link the parallel option, so having the drop after the second deployment event, having the drogue chute linked to the nose cone and the main chute linked to the lower body, and put them in parallel, one on side of the other. Other option is to use, oh, I'm sorry, could you go back to the other slide, please? Other option is to use the serial configuration, where, as you can see here in the right side of the screen, we'll have one parachute, the main parachute or the drogue parachute in the bottom, and then in a sequence, the other parachute. So they will be lined in a straight sequence. There are a few considerations to be made about both of these. In the serial configuration, we can have some four-body wake effects from one parachute in the other. So this is from our previous studies, preliminary studies, I'm sorry. From our preliminary studies, we can mitigate this problem by making the parachutes far away from each other enough so that there is no effect. But this, on one hand, this would make the lines very long and maybe occupy some more space. On the other hand, the sizes of the parachute cords, they affect the inflation loads time, and also the inflation loads. So if you have a longer cord, you have a smaller inflation load. So this, despite adding some weight and space requirements with cords, adding some significant amount of cords, we can probably make use of these advantages in the serial configuration. But it has to be very, very well analyzed. This effect that one parachute can have on the other, and how they will both, we can model them both mathematically and model the entire system mathematically, because it will be something very, it has to work, everything has to work very well together in this descent. For the parallel architecture, it is quite difficult to find references and study sources. So we have, in previous missions, previous similar missions and previous reports, we have missions that have done this before, but usually they section the rocket again and use a different ejection system for the main chute. So it's different than what we would do. Also, in the parallel architecture, the drogue chute would pull out the main chute by the lines, not exactly by the canopy. So it won't have the advantage of stretching all of the main chute lines before it inflates. And also this lack of material to study, to serve as a reference and to help us analyze this architecture is it's very, very heavy weighted on the factors, because also, okay, so we can pass on. Ter enough matéria. So for the main parachute, we have decided to use the annular geometry. It has a very high estimated drag coefficient, and it would allow us to get a very small parachute, occupies a small volume inside of the rocket. And this geometry, it generates a lot of vorticity on the flow below and after the canopy. So this change in the flow makes this geometry very efficient. So the basic difference between them is the reefing chords. Is these chords tied in the middle. So the annular will have the reefing chords, and the hemispherical don't have the reefing chords. It is the principal difference between them. And these reefing chords, they can also act as a structural reinforcement for the annular geometry. However, the hemispherical, it's a little bit less efficient. It still has a good estimated drag coefficient, but it's a bit less efficient. However, it's simpler to build. If we're going to build the parachute ourselves, it hasn't been defined yet if we're going to build it ourselves or if you're going to buy it from a manufacturer. But if we're going to build it ourselves, this reefing can be very complex to fabricate, to manufacture. So this is the great advantage of the hemispherical. They are very, very similar amongst each other, and this small difference can increase the drag coefficient greatly. So next, please. Okay, so now I've tried to introduce and explain how the separate parts work. And for the conceptual designs, we've assembled everything together in one assembled system. So I hope that it was clear and very illustrated for everyone how this is going to work. And now for the overall operation, the first conceptual design uses a parallel architecture after the second deployment event, and a release with the servo motor, a hemispherical drogue chute, and CO2 to make the hatch opening to eject the nose cone. Next, please. So here we have the pros and cons of the mechanism. My intention was to put the most important points from these small assemblies, the pros and cons of these small assemblies, and mostly the cons, the little problems that we know how to mitigate, that are avoidable, that we can solve in project, they are not really included here. So this is a pros and cons, and mostly the cons. They are presented with it's the cons that we cannot we haven't found ways to solve, or that we believe that we cannot really solve. So here, since we have the CO2 ejection, there is no heat generation of any kind. This is very interesting. The release mechanism can be repeatedly tested because all the parts are reusable. And the canopy geometry is slightly simpler to build. So for the cons, we have that this release mechanism in this specific assembly that we have put together here, it's an adaptation of other devices So this device, the way it is mounted here, has never been tested, as far as we know. So we as much as it seems like a robust design, it's a factor that lowers a bit the reliability. The parallel architecture increases the risk of cord entanglement in the descent, since we will have the nose cone and the lower body side by side, let's say. The cord entanglement is greater in the descent. So the less effective canopy geometry makes a bigger projected area for the drogue chute. And the montage to test the parallel architecture is highly impracticable on ground. So it's difficult to achieve that type of montage to test it and analyze it and model it before flight. And as I have mentioned before, the scarce reference of material for the parallel architecture is something that weighs greatly as well, because references go a long way and help a lot. And all of the references that we have some references, some projects, similar projects that have done this before, but they don't talk about it. Talk about this specific part with details in their reports. So it's scarce. The reference material is scarce. The CO2 cartridges from the ejection system, they present a high manufacturing complexity, and if we choose to buy them, they are very costly, and we can only use them once. So if we're going to test the whole pressurized CO2 system, we are going to use the cartridges every time we test. We're going to use new cartridges because they're not reusable, and the cartridges are quite costly, and they cannot be they are not imported from another countries. We can buy the systems, the puncturing interface, the puncturing system, we can buy from international manufacturers, but the cartridges are not sent internationally, mailed internationally. And the parallel architecture also increases, it makes it harder to avoid the collision between the nose cone and the lower body. It's like previously said, having the nose cone and the lower body side by side makes, without being able to model very well and test this architecture, it's a great risk. So, in the next one, we use the black powder hatch opening with the annular drogue chute and the parallel architecture, the servo release, and that is. You can go for the pros and cons now, please. So some things are similar, so the release mechanism can be tested. It's the same release mechanism. The pyrotechnic ejection module, the ejection module changes in this one. So the pyrotechnic ejection module, it can be reused. It's at this point of the project, it's hard to quantify how many times it could be reused, but this interface where we will place the powder, it can be reused a few times at least, and that allows to test, to make a model test and test them a few times, replacing only in the full separation test, we would only need to replace the black powder and the shear pins, which are quite cheap and very low cost. So it would make the ejection testing a lot more practicable and low cost. And the annular geometry gives us a small projected area for the drill chute. For the cons, we have the same as before, that the release mechanism hasn't been tested before. And we have some heat generation in ejection. This is always a problem with the pyrotechnic ejections. And there will be heat generation. However, this I believe to be a solvable problem. We would need to protect the drill chute from the heat because it's relatively close. But in this montage, the amount of black powder needed is very small. So it would be a very, very small explosion with small heat generation. Okay. So here we have the same problems for the parallel architecture, which are the scarce reference and the risk of collision, the risk of cord entanglement, and the impracticable testing for them. And for the drop geometry, the annular canopy presents a higher building complexity. Next, please. Well, here we have the Conceptual Design C. It uses also the black powder as a hatch opening, and it also uses the annular job as the job chute. But for the configuration, it uses a serial architecture and the line cutter release, which is the system that melts the line. So next, please. So here we have many pros for this conceptual design. The release mechanism can also be repeated, tested. The only destroyed item would be the line, and this is also very cheap and very replaceable. So the release mechanism can be repeatedly tested. The serial configuration is viable to reproduce on the ground for testing. It's easier to reproduce the serial configuration. The models built to fly. This is very interesting. Only this conceptual design has this item, this advantage. The models that we build to fly, they can all be tested on the ground. So the serial architecture montage is testable. The job chute is testable no matter what. The black powder module can also be tested, and replacing only the black powder and shear pins. And the line cutter release can be tested as well. So all of the models, the same models that we build to fly, they can be tested on the ground before flight. And I think that is a very interesting advantage. We also have a smaller projected area for the drill chute because it's annular, and as before, the pyrotechnic ejection module can be reused. This release mechanism, it's simple, it's easy to build and to mount, it's lightweight and small. So it's really quite simple, this mechanism. With the serial architecture, the drogue chute may be assembled to stretch the main chute cords before it inflates, relieving the inflation loads. So this is the method that I mentioned before, referred to in some of the books and references as lines first method. So the drogue chute acting as a pilot stretches the lines for the main chute, and then the inflation modes are relieved. They're smaller when the main chute opens. For the cons, because of the architecture, serial architecture, we can have a possible for-body effect in the drogue chutes. This relation between the drogue chutes, there could be one could affect the other, and the heat generation in the nose cone ejection due to the black powder, the pyrotechnic ejection as well. It's a con, and the annular canopy also presents a higher building complexity. So, next, please. For the conceptual design D, quite similar to the previous one, using the same release mechanism and the same serial architecture. The drogue would be with a different geometry, and the hatch opening system would be CO2, the compressed CO2 cartridges. So next. Here, this one has quite a few pros as well. There is no heat generation and ejection, and these are all repeated because we have we used all of these smaller parts in the previous conceptual design. But there is no heat generation in the ejection because it's with CO2, and the release mechanism can be repeated, tested. The serial configuration is also viable for ground testing, and the release mechanism is simple and easy to build and to mount, and lightweight and small, and opens the possibility for the lines first method with the serial architecture, and the canopy geometry is simpler to build because this is the hemispherical one. For the cons, have a bigger projected area for the drogue chute, the possible effect of the parachutes, the parachute configuration, and the CO2 cartridges present a high manufacturing complexity and cost, as was also mentioned before, and they are not reusable. So this is a bit of a difficult for testing. So that is it. These are the 4 conceptual designs that we have assembled. It's this assembly, they are not excluded, so we don't have to make necessarily have to make specific combinations of the smaller assemblies. We chose these because they seemed interesting for us, but I think that is if some of the smaller subassemblies if you would like to change some of these smaller subassemblies, that would be completely possible too, because there is no restriction for linking one and the other subassemblies. They can all be combined together. So that is it for the recovery presentation.
So I have no words. Just a second here. Now I can talk. Sorry, I was without a return for the sound. I have no words to say or to talk right now. The work that you, Sarah, and your team, and the record. that I listened tonight. I think the most complex designs, the most complex thinkings, like thoughts, is developed by your team. It is something very nice. I have no words. We have a lot of decisions to make. We have a lot of things to decide. The safety is our value number one. Recovery. So recovery is very important. We would like to launch the rocket and recovery safely the rocket. So the decisions are complex. We have a lot to talk. But before it, I would like to ask if Alexandre, João, Yamato, if they have any comments to do right now, to make right now.
Yes, thanks, Calvin. Sarah and Phoenix and all the team that work on the subsystems. Congratulations for the design. As Calvin said, recovery is one of the most important phases of the flying a rocket, because if you didn't recover the rocket, your mission is not complete. And you did a amazing job on the technical drawings and also design the system, showing us different possibilities. So different types of ejection system can be used, like CO2 can be used, black powder, also for the trigger of the main shoot mechanism with some pyrotechnics and mechanical designs, very good. And as Calvin said, probably there are some ways that we need to figure out which one is the best to fit for this project. But congratulations for the presentation.
Alexandre, do you want to make any comment?
Alexandre, you are muted, so we can't hear you.
Alexandre, you are still on the mute.
Still muted, Gular. Check your headphones mute, something like that.
João, you can talk meanwhile.
Yeah, I like to say that the designs are like impressive. I liked a lot what you proposed here. The system for releasing the latches and everything are like very great. The way you designed it and the team designed it, everything is like very good. The part, I love the white part that you displayed here, the 3D printed I think part with the maybe nylon or something to cut the nylon. The system is like very good and was very well thought, and it's really clever engineering. And what I think you can maybe use to choose between the paths we stated here is that always present engineering concepts of the KISS method, right? They keep it simple. With recovery, I personally think that the simpler the better with recovery systems. So I loved everything. It's really good and great engineering. And you can maybe try to pick the simpler system between those ones. As you said, like the CO2 or compressed gas method has some cost problems. Some other method has other problems. So this was very good work to point out this. I've personally never seen, for example, the CO2 systems. I've never seen them personally, and I think they are very like expensive because of what you said. The recharge of the system is like very, very expensive, and I think the simplest method is the the one that uses fire, right? The black powder method or the hot wire method, they are really great because they don't rely on another unknown thing that has to puncture a hole in a CO2 device and some other things like that. Is Alexandre back? I think
Yeah, I'm back now. Everything's working.
You can
Yeah, can you hear me? Okay. So, well, I was, well, I haven't even started, right? So first, congratulations on our presentation, all the work you've developed. I know, I think that for your subsystem, there are not a lot of people, like a really big number of people. So that's really a lot of work. It's pretty evident that it was a really extensive research to get all this information, all this design. Of course, there are some points to be enhanced, and which are really critical since it's the recovery is such a especially important safety concern. So I think the other guys already said there are some points there we're going to tackle on another opportunity, but especially concerning the physical, the mechanical part there. But congratulations, and also I'm especially more a fan of the parallel line because it's more a convention, more of a conventional design. But it was really interesting to see the information you brought about the serial too. But yet, I believe the more conventional usually is better. You get a higher reliability. That's it. Thank you.
just commenting here that Yamato said that I was talking about a lot of Lero, but it's not. And he sent me a link that I accidentally clicked here on the screen, but it is not like Lero. It's really great engineering, and I'm basically speechless, and I think Goulart is too. And it's a lot of work. You can basically think in terms of she presented here and the system presented here 4 options, and other systems presented like 2 or 3 maybe, but these were really great and profound and deep 4 options. So it's really like something unbelievable.
Thank you, guys. Thank you a lot. Your comments will help a lot, Sarah and the team, the recovery team. Something that I would like to say, like Artur Magalhães said in the comments of our live stream on YouTube, the presentation was speechless. Sarah and the recovery team, we will ask you guys for an internal meeting for discussions, and we will together talk more on the positions, and we will talk more on the designs, and of course there we will talk on a decision making for the concepts. Okay. The work was impressive. Congratulations.
Okay. Thank you very much for all the compliments. I'm very happy that everyone liked it so much. I would like to clarify one thing from the recovery presentation that I didn't make it clear, and I don't know if might end up being misunderstood. So if you could please return to the previous slide, to the architecture design. Here, I would just. Oh, Okay, so yeah, this one. I would just like to clarify that the serial one, I forgot to mention this, but the serial one, here it's an illustration with two clustered parachutes on top, but this is not our design. This is just to illustrate, and I had to mention this on the beginning, and I forgot. So this is just an illustration because I couldn't find one that was exactly how our design works. So this is a serial of one parachute and on top two clustered parachutes. Our design is to use one parachute below and one parachute on top. So it's a simpler design. And I would just like to clarify this because I forgot to mention, and I wouldn't want to have any confusions or anything like that.
Thank you, Sarah, for your clarification. It was a nice clarification for the general public. Nice, congratulations to the recovery team. Now, like we said before, we will talk more internally about the recovery system. We have a lot of decisions to make, and we need to talk. The work was impressive. So it's already 3 hours or 4 hours. 4 hours since we start our system design review. We talked about the propulsion system, structure and aerodynamics, avionics, recovery. For today, or for tonight, I would like to end our meeting. We will not be talking about the payload tonight. This is a too long meeting, so we can talk about the payload in an internal meeting in the following week. So I would like to be thankful for the payload team. I read your presentation; it's impressive also, but it's be nice to talk about the payload in the next week. So I prefer to end the meeting for now. I will ask Vinicius Fernandes for a final comment about the engineering systems team and for the final comment about our system design review before our final word from the LASC side.
Okay, thank you very much, Calvin. Thank you very much for everyone. The January level here was very high. And I would like to thank you, two guys that are here around, Breno Rosada and Rafael Augusto. They are the leaders of the engineering system team. As I said during the presentation, many interfaces and connections between subsystems were presented. A rocket is an integrated system, and everything must be harmonized and tuned to work together and good. And his duty goes to the system engineering team, led by those two fellows. They've been my great helper with the tinkering and adjustments between the subsystems, and without them, that team would be light years behind. And thank you very much for those two and the engineers, the system engineers team. Thank you very much, Calvin.
Thank you, Vinicius. I would like to thank Rafael and Breno Rosada. The work that they are doing is amazing also. Thank you, Breno and Rafael.
Thank you, Calvin. Thank you, Vinicius. It's my pleasure to be a member of this great project. And first of all, I would like to say that I am very grateful for the progress of the project. And what's that? Thank you.
I'd like to thank you too. Actually, thank you, Calvin. Thank you, Vinicius too. It's a pleasure to be here in the project too. And I hope to work more with you. And actually, I'm pretty excited with the project, with all the presentations that were presented here. So
again, thank you for being here.
Thank you, Rafael. Thank you, Breno. Before we end the meeting, I will pass the word for the evaluation committee. If Gabriel Yamato would like to start to your final comment.
Yes, thank you, Calvin. Thank you all for joining us today. Really, all the presentations that we had was really good, and we had some homework from both sides to better improve our designs and get step to step closer to our launch in 2021. So this is the first meeting that we had for a complete review, but of course will be other meetings that we are going to go deeper and deeper on the subsystems. And thank you very much for everyone that's joined today, the ones that are commenting on our YouTube live. It's always great to have the feedback from the people that are watching and participating, making questions, and thank you all.
Thank you, Gabriel. Thank you for your presence here and your comments. It's a pleasure to have you here. Now I will pass the word to Alexandre Goulart.
So thank you, Calvin, and I would like to thank first everyone from every subsystem, and because we are really in a very intense engineering task, and see that every week things and the designs are getting further and further, more complete, more interesting. It's very, very good, and I should congratulate everyone for your work, and also thank for the viewers who a couple of them have even participated, made questions. That's something that really is really rich to have here together in this meeting. And that's it. Thank everyone also for the opportunity to be here together with you. Thanks.
Thank you, Alexandre, for your time. Thank you for your comments. It's a pleasure to have you here also. Mateus Cruz, are you still there?
Yes, I'm here. Can you hear me?
Yes, I can hear. I can hear you. Could you make your final comment?
I just want to make a brief comment. I want to congratulate everybody. The project is exceeding expectations, especially in this moment we are living, where most of us are having to work from home. And I believe this is going to be a great project. Congratulations.
Thank you, Mateus. Thank you for your presence and your comments. It's a nice and a pleasure time with you here. Now I will pass the word for your final comment, João Pedro Vilas Boas.
Hello again, everyone. Thank you, everybody, for their presence here. It's always a pleasure to control everything here on the stream. Let me just remove the name. And it's always a pleasure to hear everyone here talk about rockets. I think everyone that is here loves rockets, loves working with rockets, and loves everything related to the subject. So thank you again for the work you've put into today's meeting. It was awesome. We had something around 100 slide pages that we had to go through today, and we went through them, and this was really, really awesome. Every one of these pages was prepared by everyone inside the cooperation program. This is something really cool, I think, because we had basically a lot of people working together to present something here. So that was really, really nice. So thank you everyone for their participation here. And we expect to hear, I at least, and we from PION and LASC, we expect to hear more from the LASC Cooperation Program and the very nice work you guys are doing here. Thank you.
Thank you, João. For our final comment from the LASC side, I would like to congratulate every single team member, every PMO. We had tonight a great meeting, a technical meeting. It was a great time to discuss about the rocket. Rocket is not simple. It's very complex. For example, last week we had 2 commercial rockets being launched and both failed. For example, it's not simple, and this kind of design review, it's important as milestone for our development and for our safety. I would like to thank André Benoit, Augusto Lima, Breno Rosada, Bruno Gatti, Christopher Deep, Elmo Brandão, Felipe Bogaerts, Heloísa Lemes, Igor Noves, João Fleury, Larissa Silvia, Lívia Bartoli, Lucas Furlan, Rafael Cota, Rodrigo Oliveira, Sara Rodi, e Vinícius Fernandes, that is still on the PMO meeting since 19:30. It's almost 4 hours and a half. So thank you, everyone. Thank you, your teams. Now we are almost go for the next meeting, the preliminary design review in a couple of months. So thank you all. That's it. See you. Good night for everyone. Thanks.